Okay, welcome everyone to day 3. And today we're all gonna learn how to do data assimilation. Woo! So Jonathan will be leading the charge here and walking us through the tutorial for the day. Hopefully you all got the email and have downloaded MATLAB at this point and downloaded the package, got that installed, the dash package. If you have any trouble doing that, you want to do that now. And then do you want to explain, Jonathan, the sort of sticky note system and everything?
Yeah, I'll hit that up when we maybe get to the first coding session. Turn this up. It's on. It's on. All right.
Yeah.
I can.
No, just leave it on. Yeah.
Okay.
Okay, sounds good. All right.
Go away.
What do you? Oh, your toolbar. Yeah.
Oh, there we go. Okay. No. It might just be Zoom. I'll work on it. It shouldn't matter too much. But okay. Hi everyone. Welcome. Thanks for coming to the to the workshop. Just as a sort of basic layout of how I thought we'd do things today is, we have this dash toolbox, has a number of different components to it. There's maybe a bit of a learning curve to the different components. So kind of going to go through alternating like a short lecture about a component, just kind of like how it works. And then we'll do like an open coding session with some demo data sets to let everyone practice using the commands in the toolbox. Yeah, so last night I sent out these prereqs. Just wanted to check to make sure everybody was able to do that, do these successfully. I know Kevin mentioned issue wherein you couldn't double click to install. So anyone else had that issue? You put a line of code in the email. Yeah.
Sorry, unrelated, sort of related, another tech issue. Is anyone else having issues with Wi-Fi? I can't very fast.
Yeah.
Okay, cool. Because I've been on it the last couple days.
Do you have EduRoam? Because EduRoam is much.
EduRoam wasn't.
Yeah, it has.
UAGS is more consistent than EduRoam.
Ooh,
Like
okay.
UAGS, the quality tries.
Okay.
Okay.
Trying.
I think for the most part, people, it would be nice if you could, if you'd be able to access like the website pages to walk through them. Apart from that, I think everyone should be able to do everything offline. There's a demo data set which we can pass around on a thumb drive if people are having trouble connecting, but yeah, let me know. And so I'd encourage everyone to go ahead and go to the tutorial website itself, because that's kind of what we're just going to be walking through today. I think I sent out the link in the email yesterday, so everyone should have that. Yeah, so I thought we've talked a lot about data assimilation the last 2 days, but I thought it might be nice to do like a little primer and just overview of how it all works, especially kind of looking a little more at the nitty-gritty of what type of data you actually need to throw into an assimilation code. So yeah, if anyone has questions lingering from the workshop the last few days, like this would be a really good time to ask them. We've got plenty of time to talk about this, so please don't hesitate to ask any questions.
And by the way, as a reminder, the microphones in front of you are off, but if you want to turn them on, you can even leave them on. But turn them on the green.
Yeah, it'd be nice for everyone on Zoom.
Yeah.
So yeah, as we talked about, kind of in the broadest terms, when we're doing data assimilation, we're trying to combine climate model output of some sort with some proxy records. And we'll often denote these as X for the model output or the climate state, and Y for the proxy records. And so, we can sort of express in the broadest terms, when we're doing an assimilation, we have this equation, XA is some function of XP and Y, which is to say an updated climate state is some function of our climate model output and our proxy records. And so I'll kind of little note on terminology here. We'll often express the Kalman filter or the particle filter in kind of Bayesian terms. And so, yeah, we'll often call the initial climate model output that we start with, call that our prior, and updated output will be our posterior. So in terms of actually implementing data assimilation, we're going to be working a lot with state vectors. And so the idea here is that, we're going to take climate model output over some period of time, not necessarily on a spatial grid, but possibly on a spatial grid. And we're going to reshape all the data from that point in time into a long vector of data values. And this is a state vector. There's no strict definition of what needs to go into the state vector. It could be a global temperature field. It could be the Niño 3.4 index. It could be some ocean variables. But often it's going to include data for one or more climate variables and possibly a set of spatial points. Another thing you might see in the state vector is like a trajectory of successive points in time. So for example, you might have data from the temperature field at different months of the year, or again, using like the temperature field as an example, you might have data from several years following a volcanic event. But ultimately, what the state vector is doing is it's serving as like one possible description of the climate system for some period of time. Any initial questions there?
That makes sense what's happening here. Just compressing the 2D stuff or 3D stuff into a vector.
Yeah.
One giant file.
And yeah, that vector is essentially a single point representation of climate system. So kind of most of what people have been talking about in the workshop have been ensemble data assimilation methods. And so the idea here is we are going to get data from many different states in time, and we're going to collect them into an ensemble. And ultimately what this is doing is it's giving us a probability distribution of possible climate states. We talked a lot about climate model biases and how they can affect things, but assuming that our climate models are doing reasonably well, then this ensemble is giving us a spread for what we think past climate could have been. And then kind of as a technical note here, when we're selecting our different ensemble members, we often select them from different points in time in case of a stationary prior. We might select them from different members of a model ensemble in the case of like an online assimilation or an evolving offline assimilation. Or in some cases, you might select ensemble members from both. Kind of hybrid. Yeah. But yeah, so typically when we're running a DA algorithm, then we're going to be taking, let me go back to the figure here. We're going to be taking all of these ensemble members and we're going to be comparing them to our set of proxy records. And ultimately, we're going to try to update these ensemble members so that they more closely resemble the values from those proxy records. So a lot of people use the metaphor of comparing apples and oranges through the workshop, and I really like that. Because the question kind of comes up, if I have a tree ring record, how do I compare that to a temperature field? Or if I have an icicle record, like how can I compare that to a global representation of the climate system? And so the way we're going to do that is using proxy estimates. And this is where our proxy system models, which I'll often refer to as forward models for the rest of the day, because a linear PSM is like maybe not actually a proxy system. But what we're going to be doing is we're going to run forward models on each ensemble member here. And that's going to give us a set of proxy estimates for each member of the ensemble. So yeah, just kind of going through the figure here. Maybe I had a tree ring PSM, and I would run that on each member of the ensemble, and I would get a potential tree ring record value for each member in that ensemble. And ultimately, what that's going to allow you to do is to compare your real proxy records to our climate ensemble. And so kind of a term that will pop up a little bit today is the innovation. And the innovation is the difference between our proxy estimates and our actual real proxy records. That difference is how we're going to say, oh, this ensemble member, it looks not very much like the proxy records. Maybe it needs a lot of update. Or hey, maybe this yellow proxy estimate looks very similar to these real proxy records. And we can say, hey, the yellow ensemble member, that's probably a more accurate representation of past climate. Kind of written formally here. This is the y minus y hat term that you'll often see in like the Kalman filter update equation or in the particle. Yeah, so we also talked a lot about proxy uncertainties in the workshop. And so kind of expanding our data assimilation update equation here. When we're doing an assimilation, our reconstructed update climate states, they're a function, yes, of the initial climate model output prior, yes, the proxy records, but they're also a function of how uncertain we think the innovation is. And so kind of for paleoclimate applications, our largest uncertainties, they're not going to be they're often not measurement errors. Like for example, I can look at a tree ring and I have a very good sense of how wide that tree ring is. Like the measurement error is very, very small. But the real uncertainty often comes from running forward models. We know our forward models are much more simple than reality is. And yeah, so that's typically where a lot of uncertainty is added into the assimilation. Yeah, another point kind of made here is also if you think your proxy record is noisy, and a noisy record of climate, which is typically true. Typically, there are local effects that will affect the proxy record. That aren't directly related to your target climate field. Your R term should also account for that proxy noise. So yeah, today's tutorial, we're just going to focus on using a Kalman filter as I think what a majority of us in the workshop use. I know Hughes is true, uses particle filters a lot. We can touch on them at the end of the day. But for the Kalman filter, I thought it might be useful just to kind of walk briefly through the Kalman filter update equation and what these terms are and how we're going to kind of calculate these terms through the day. So yeah, for the millionth time, here's kind of the Kalman filter update equation then. We have our updated climate state is going to be that initial prior ensemble plus some sort of update. And this update is going to be that proxy innovation weighted by the Kalman gain matrix. So kind of looking at the Kalman gain matrix here a little bit more. This is going to be a function of several covariances and also those proxy uncertainties. The first covariance we have to consider is the covariance of the proxy estimates with the target climate variables in the state vector. You can think like, okay, let's say I have, an innovation here that says that my proxy estimate is 5 units too cold. I could then look at like the covariance of the proxy estimate with the target variable and say, okay, when the proxy record changes by 1 unit, then the temperature at this grid point goes up by, 5 units, let's say. So if I had an innovation of, hey, my ensemble member is looking 5 units too warm, then we'd want to update temperature at that grid point by 25 degrees or whatever. So that's kind of the the numerator term in the Kalman gain. This is all matrix algebra, so I know we're not supposed to say numerator and denominator, but I think it's really useful to think of it that way. So that's what I'm going to call it. But then you're going to take that covariance and you're going to weight it by 2 things. The first thing we'll weight it by is the covariance of proxy estimates with one another. You can imagine if we had 2 proxy records that were right beside each other, and we were like 100% certain that there were like no uncertainties in those proxy estimates, we wouldn't really want to do we wouldn't want to use the covariance from each of those proxies with the target variables twice, because we'd sort of be doing a double update. We'd be representing information, like the same information twice. And so this first covariance term here in the denominator is kind of accounting for that some of the proxy estimates might be covariant with one another, and we don't want to like duplicate information. So then the second term that's in the denominator is that proxy uncertainty term that we talked about so much in the workshop. And this is saying, okay, maybe I have some proxy innovation, but I'm really, really uncertain that this innovation is a accurate comparison. So if there's really, really high proxy uncertainty, maybe I'll do a smaller update there. Instead of updating by 25 degrees, I'll say, okay, it probably should be warmer, but I'm not sure it should be like 25 degrees warmer. We'll just make it 5 degrees warmer, or what have you. Yeah, so you don't need to memorize this equation with the workshop, but these are kind of a lot of the terms, a lot of these inputs here, the prior, the proxy estimates, the uncertainty values. These are kind of some of the data values that we're going to need to use with the Dash toolbox to like actually implement the assimilation.
Question?
Yeah.
Sorry about the common filter.
Absolutely.
So you have two different.
Do you wanna use the mic?
It's on.
Oh, awesome.
So variance of the proxy estimates with the target climate variables. So you're comparing two different state vectors, basically.
The proxy estimates with the target climate variables. Sort of, yeah. Like if you think about it, I'm really visual and I like always have to sketch things. So
Yeah.
You might have.
Can you use a platform?
It doesn't.
Oh, I have one.
Okay, cool.
Just to clarify my question, I'm confused how that works compared to the other covariance and proxy estimates.
Yeah.
Which
Okay. Well,
which seems to me within one vector.
right. Maybe without even sketching things. That first covariance, I think it would be more accurate to call it a cross covariance, if that is helpful in any way. So you can think about, maybe I have like, should I stand on here? Oh,
You're still
okay.
in the camera.
Yeah, okay, so maybe I'll stop screen sharing.
Yeah, it can also, yeah.
Yeah. So I might have like, this is my state vector. It's got a whole bunch of climate variables in it. And I actually have an ensemble, right? So is that visible? Is that dark enough? Or... So I've got some sort of ensemble. These are all climate. Yeah. Can people see this? I can use the red marker. We can see it in here. Yeah. People on the Zoom chat. I see
it a little bit.
I see some photos.
Okay.
Okay, great.
If they open speaker view, it should larger.
Oh, yeah.
Oh, yes. Sorry, I thought.
No, they can see you. That's fine. Yeah, they can do it.
Cool. So, right, so we might, for that first covariance term, we have like some long climate state vector, and we'll have a second ensemble of the proxy estimates.
Right.
This will typically be a little, it's probably shorter. Like if I have a full temperature field, I might have thousands and thousands of data points. I might have like, I don't know, 100 proxy vectors or what have you. So like, then we have, our shorter ensemble. I can't draw in straight lines very well. And these are our proxy estimates.
So where does the ensemble nature coming from for the proxies?
Yeah, so if
So I
you
think
remember
that one line works, maybe you only have 100 measurements.
sure, but like how did we get to an ensemble? So that's where those forward models came in. So let's say I have, here are my down here are my actual, you see down here?
Yeah.
Here's my actual proxy records. And this is like for a single step in time, I've got this little short vector, right? And I need to compare this to all these different climate ensemble numbers. And so that's where the forward model, the PSMs are coming.
Okay, so proxy estimates are the results.
As a result of PSMs.
Okay, it's not the original data.
Yes.
So where you have proxies in the long X matrix, you are generating proxies that end up in a shorter Y hat.
Yeah, so kind of writing in my variables here, this is Y hat, this is Y. These are the estimates of the real proxy records. for each of the ensemble members.
And you can do the covariance because you have the same column.
Right, you have the same number of ensemble members in each of these matrices. You know, I have for each climate member ensemble, sorry, for each ensemble in the prior, I have, you know, one set of proxy estimates for that ensemble member.
Okay, that makes more sense now for that. So then the second covariance and proxy estimates for each other.
So that's taking, you know, this matrix up here and just doing a matrix covariance of that one directly.
Okay.
Yeah.
Okay.
Yeah, so the first covariance term is more truly a cross covariance of this X and Y hat. And the second covariance term is like a true covariance matrix.
Okay, that makes sense. Thank you so much.
If you guys give me 1 second, I can show a figure that
Yeah, absolutely.
explains some of this a little bit better. That I'll just project it up there.
Yeah, totally. I'll just do this.
Let me just. So.
So if you've got, say, 40,000 climate points and 100 proxy points. With an ensemble, let's say 100, I cross the variance matrix is that 40,000 by 100.
Yeah, right.
So what's the size of R? So that's gonna, at the bottom then you've got the covariance,
Right. So R,
100 by 100.
yeah. I think Jess's figure is almost here. So let's do that first.
I just want to, for you to, so I'm actually showing you the Kalman gain as a numerator and denominator, because as Jonathan said, it's a little easier to think about that, even though
It's a useful thinking frame.
it's matrix algebra, right? But here's, so, minimize this. Okay, so this, what I like about this figure, which that Badger made, not me, but I've been using it in all my talks, right, is this explains what's happening in the numerator covariance calculation. So if you have a proxy record in Seattle, right, and then you calculate the covariance of, this is still a model world, right, the estimate of what the proxy is in Seattle with the entire state vector, let's just say it's air temperature. This is the pattern you might get. Actually, it's probably correlation as signs, right? But the point is if you make an update here, you will also update over North America, right? Where that you have strong covariance. You also update the other direction over, or maybe over the Pacific Ocean. So in this way, this numerator is spreading the proxy information around. And that's one of the power, right? It's because now your proxy is not just updating where it is, it's updating wherever it covariates, right? Now you may have heard in the workshop people talk about localization. And so when they're talking about that, you can see that actually, you know, the covariance function has some covariance over here, or even way far away in the Southern Ocean. And maybe we think it's pretty vague, but maybe we don't, we think that this is aphysical, right? This is just kind of, yeah, we don't really want to update Antarctica from Seattle.
Yeah.
So,
Usually it's like, I think we usually call it a sampling bias. Like we have a finite ensemble, so we're gonna get the covariance a little bit wrong, as opposed to the perfect, true, infinite sized ensemble.
so we're not gonna do localization today, but just, you know, it is basically.
Oh,
put
we
it-
are.
Oh, we are.
Yeah.
We do a halo right around here, and say, beyond a certain radial distance from my proxy, I'm not gonna update. That's all it is. So there's this, people do that in DA just to eliminate these far field things that maybe you don't wanna update. Does this help visualize what's happening? Okay, and then these are just the error terms. You can think of them as the error terms, although I like Jonathan's explanation of this will also downweight. Like if you have two proxies in the same place, they don't get double counted because they have such a strong rate denominator. So if these values are higher, full update is lower, right? If your proxy is more uncertain, full update is lower. So hopefully that helps.
Then R must be a square matrix,
That's right.
the
Yep.
same
Yes.
size as the covariance of the YEs.
Yep.
So let's say we have 100 proxies, 100 by 100, R is 100 by 100 with the uncertainties on the diagonal.
Yes. So Yeah, let's talk about R.
There's a question in the chat.
Oh, yeah.
A good question.
Let's
Do you
see.
want to answer it or I can answer it? Oops.
I'll just read it. So Hunter asks, so the only real proxy information that's encoded into the Kalman filter is R, the uncertainty of proxy data. Otherwise, proxy data is in y minus y hat.
Yes. Well, the forward
Well, I would
model,
say that y, I would say that the y term is real proxy data.
yeah, that's what I think he's saying, but
Yeah.
the real proxy data is Y. However, the forward model is YE, so it's not proxy information, but it is your statistical model of what you think the proxies are doing.
Yeah, so yeah, Jess raises a really good point. So there is a little bit you could say that there's also proxy information in the covariance of the y estimates and also the covariance of the estimates with the climate state, but only in the context of we've tried to estimate these climate proxy records as best we can using forward models. Like only after we go through the forward model process, like whatever proxy information is remaining there, is being encoded.
Do you guys have more questions about this?
I think Kevin, okay. Well, so Kevin brought up the R matrices. And so it's also going to be, so we mentioned that when we do the covariance of these proxy estimates with one another, that's going to be a square matrix. Cool. We all kind of, I think most of us hopefully understand what that covariance matrix look like, symmetric, the variances are on the diagonal. The proxy uncertainties is also going to be a square matrix, and it's going to describe the covariance of errors between the proxies with one another. Might go ahead and erase this. So if we have our R, this is going to be some square matrix. And in a lot of approaches, we'll make the kind of assumption or the approximation that the error in one proxy is probably independent of the errors in all the other proxies. And so when this is the case, R is a diagonal matrix. It has the error variance for each proxy independently on its own. But everything else will be 0. We'll be saying, okay, I don't really think that the local errors or the forward model errors for proxy 1 are affecting proxy number 2 in any way. So yeah, we'll often use our variances, and that's kind of what we'll be working with today tutorial. Although I think Nathan brought it up in the workshop, is that you can also as you start to get proxies that are perhaps very close to each other or very strongly correlated with one another, or maybe you're doing replicate proxy records from a similar site, then it might start to be that actually their errors and their uncertainties do have some covariance. And so if that's the case, then this isn't going to be a diagonal matrix anymore. You'll need to, when you do that, you'll need to find some way to quantify the covariance in the uncertainty of the proxies with one another. So maybe proxy number 1 here, and proxy number 2, maybe they're replicates from a similar site. So we think that the problems, if the forward model has a hard time estimating proxy number 1, then the forward model's probably gonna have the same issues with proxy number 2, and so their errors will be covariant, and so we'll start to fill out this matrix, and it'll have values. Yeah.
To be fair, most reconstruction methods that are less simpler than this also assume that this is a diagonal matrix.
That it's a diagonal matrix. Yeah, I'd say it's pretty common in paleoclimate, but I mean, this is one cool thing about data assimilation is we do actually have this option to do full error covariance to see if we can get these program. Yeah. And I'll so again, but anyone else?
Is this something that you sort of have automated in a way at Dash at this point? So
Yes.
that we could maybe explore it.
Yes. I'll kind of note here, generating this, the actual values in your uncertainty matrix, that's going to be one of your large, scientific decisions that you as a user will make. Dash will, give you tools to calculate it, using the data that you think is appropriate, but ultimately you're gonna need to decide like, okay, how am I going to estimate proxy uncertainties? Am I gonna, pull it from the forward model in some way? Am I gonna compare, like instrumental? Another way you do it is to run like a forward model on instrumental records. If you're like in the common era, and you can compare those proxy estimates to the real proxy records. Like, there's different approaches. Yeah, it'll be something that you'll have to decide how to do. But we'll try to give you the tools to do it at least.
So also the assumption here is that R is unchanging. You kind of mentioned this in your talk, but
Well-
basically, because because all the other matrices are ensemble matrices, which basically says, okay, for that ensemble that's up there, this is the R value.
Yeah, so that's a great point. My comment here is that in all of the assimilation reconstructions that I've seen so far, we've always assumed that these are fixed because I'm not sure we necessarily have the data to do otherwise. I think Emily, you mentioned like as you go deeper back in time, some of your proxies may become more uncertain or have different errors or uncertainties.
Yes, I take a really different.
Actually,
I take a really different approach with R because some of our sensor models that we're using aren't Bayesian, so I don't get an example out of them. I don't have a way of happening it, so we do it consistently. I did a series of sensitivity tests with data closer to the modern where I had that understanding of reality a little bit better. And played around with essentially iteratively, systematically decreasing in XR and looked at different skill metrics across that. And then what I came up with is kind of a low end, a high end, and like a Goldilocks R value for each proxy system. And then I assign my R. So I take like the lower third percentile of data that had the fewest number of data points that I'm averaging. They get the highest uncertainty. Then my middle third gets the Goldilocks, and then the Y values that I'm averaging from tons of data, and I feel like I'm converging in on a better mean value. Those get us the lowest uncertainty, and so that's how I do it. But then those low, medium, and high also change through time, and so as you go back further in time, right, you have uncertainty related to diagenesis and things like that, but you can't really totally quantify, but you know exist. And so I scale up each of those R values to like a back in time, so that each data point is kind of contributing a little bit less weight.
yeah, that's awesome. I will also comment if you want your R values to change through time, like Dash has that functionality. You can set it up to do that. So, yeah.
Just a following up
Yeah.
question so you said that for paleoclimate EA, we generally have diagonal R matrix. But it depends on the size of the pixels, and for an example, you could have more than one site in that, like 1x1 degree climate model outputs. The R not gonna be that.
I think I don't really think it pertains to the model resolution. It's more like the resolution of reality, if you will, where you're like, I think in reality that these two records are so close together that they're essentially the same information. That's where this would like start to affect R. If you're like, hey, in the real world, these sites are close, but they're responding to completely different things, then even if they were right beside each other, so long as they're responding to different things, you could still estimate them as independent.
Yeah, like as an example, let's say you have at the same ocean core, you measure alkanones and OAT. And so maybe they probably are related in the real world, but because they're so maybe you would want to do an off diagonal, but typically I don't. I let that first term in the denominator do that work a little bit, right? Because it's like, oh, you're in the same spot, so I'm going to downweight you already. And then the other logic there is that those are totally different proxy systems, so they actually are independent. Like they're measuring like you know, that there are different sensors. So because they're physically different sensors, I usually just treat them like as they're not related. But you can build that in if you want. I guess that's what we've done. Is basically they're different proxies. We basically just let them assume that they're independent.
Alright, yeah, and the way it'll work in the code is like if you only give dash one set of R values, then it'll use it for everything, but you could also give it like a time varying set and it'll apply it to whatever times. Alright. Go back to screen share. Okay, so kind of with that kind of overview in mind, we can kind of start to outline what we're going to be doing in this workshop a little. See some of the common tasks here are going to be, we're going to need to build a state vector ensemble. We're going to need to run forward models over that ensemble. We'll need to estimate our proxy uncertainties, and then we'll actually need to run the common filter or particle filter assimilation algorithm. And I'll note that today, we're not going to get in deep to the estimating proxy uncertainties, because that's its own large scientific topic. So we're going to kind of focus on 1, 2, and 4 here. I think in one of the demo data sets, I just give you some proxy uncertainties to work with, and in the other, we'll try pulling it out of the forward model. But yeah. So yeah, kind of here's our outline today. We're going to kind of start with just an introduction to Dash as a toolbox, just a rough sense of what it looks like, how it works. And then we'll kind of take a quick look at these demo data sets. And the idea is to use these data sets to practice Dash commands over the day, get a sense for how the toolbox works, and then hopefully you'll be able to apply these commands to your own data. After that, we're going to start by building our state vector using the state vector class. From there, we'll build some forward models, we'll run them over the ensemble, and then we'll move on to running the common filter. Okay, so just going to kind of jump right into the Dash toolbox. So Dash, it's a MATLAB toolbox, and it's written to facilitate paleoclimate data assimilation. It's designed, to run from the command line in MATLAB. It's not like a giant GUI. And because it's a command line, we're typically going to use this toolbox and kind of incorporate it into different scripts and different functions as you will. One thing I'll comment on is that Dash is very much a bring your own data type of toolbox. It's not the type of thing where you're just going to press go and it will run some specific assimilation from scratch to end. Like, we're giving you the tools to do data assimilation, but you still need to make your own scientific choices, and you're definitely going to be writing code along the way. So with that in mind, like a little bit of experience with MATLAB is useful, but I will try to comment on anything we go over today. I know a number of people haven't used MATLAB as much, so it's like if there's something in the code that you don't understand what's going on, please just ask and talk about it. Yeah, but just as a really brief kind of overview of the toolbox itself, it's kind of laid out into several different components, kind of built around several different features. One of the things that we've tried to build in is this ability to kind of organize and catalog different types of climate data. So if you're thinking about assimilation, we often have like really diverse types of data. We've got like climate model output, which is maybe spread across several net CDF files, and it's on a gridded, spatial global grid. But then at the same time, we also might have a proxy data set, which might be often some text file or Excel spreadsheet. We want to combine these, and often these can be saved with different types of metadata and different types of formats. So kind of there's two components in Dash called gridfile and grid metadata that help you build kind of data catalogs, so you can kind of inhale everything all at once. Second thing it's really a focus is building state vector ensembles. So there's this state vector component, which will kind of allow you to flexibly design how an ensemble looks. We also have, once you have an ensemble, we have some tools that will help you to manipulate that ensemble. So this includes like some commands for creating an evolving ensemble. But also from a practical point of view, when you make a very large state vector ensemble, like we mentioned how you might have thousands, tens of thousands of data points in state vector. You have a large ensemble like that, it can sometimes overwhelm computer memory and everything can run really slow, or in exceptional cases, you might not even be able to load your ensemble. So this kind of ensemble component is going to let you manipulate ensembles without needing to actually load them. Just kind of this practical point. Kind of the last two then are we have kind of a section built around proxy forward models. There's an interface called PSM, which lets you take external forward models like Jess's Baywatch suite or Sylvia's Prism package and like run them on an ensemble from Dash. And we also have this ensemble metadata class, which helps you like find the data in an ensemble that you actually need to run forward model. And then the last thing that's in there are our data assimilation algorithms. Currently, we have a Kalman filter, particle filter. We didn't talk about optimal sensors much in this workshop, but that's in there as well. That's sort of it's derived from a Kalman filter, but it can help you quantify like how much a proxy is affecting a Kalman filter reconstruction. Yeah. So those are kind of some of the features. Any questions? Or yeah, we'll just kind of keep going. Oh yeah, okay.
Capabilities for doing pseudo proxy or OSI experiments.
Yeah. The way that Dash is set up is like a pseudo proxy experiment wouldn't, like the code wouldn't be any different from a normal experiment. It would just be you saying, hey, use the pseudo proxy data that I generated instead of like a real proxy data set that I run somewhere.
I guess are there any tools to generate that data set like based on
Like generate pseudo proxies?
the sample them.
Sure. I think the proxy forward model component is kind of where that would come in. If you wanted to be like, often when I think about pseudo proxies, the way that I'll approach it is I'll just build like an ensemble from climate model output over time, where the ensemble is just ordered in time. And then I'll take this like PSM kind of component and I'll run the forward models on that ensemble. And the output of that is the pseudo proxies. I hope that makes sense.
Yeah, that's
Okay, cool. So I wanted to take a quick point and just address that Dash is written in an object-oriented style. I know we have a lot of people code in Python here, so this is probably maybe going to seem pretty familiar. But we also have people who are mostly familiar with MATLAB, and this doesn't come up so much in MATLAB, so I just thought we should talk about a few terms that you're going to see in the workshop. For the Python people, Dash is hopefully going to feel a lot like using Python package. But so we're going to introduce this idea of classes. And I mentioned that Dash has all those different components in it, and each of those components is what we call a class. And ultimately, this is a piece of code that describes some sort of specialized structure. That structure might have some data fields, and it might also have some functions that operate on those data fields. And we'll call the data fields properties, and we'll call those functions methods. So yeah, and my example here is that we have that Kalman filter class, which is going to help implement the Kalman filter algorithm. And so like the properties in that class are going to be, the data fields going into the Kalman filter, but also maybe some algorithm parameters like what I want localization to look like or what I want inflation to look like. So that would be like a property. And then at the same time, the class has some methods, so it has this method localize, and that will actually, implement covariance localization. It has this run method, which will actually run a Kalman filter using the data values that you stored. Kind of the next step of this is an object. So an object is a specific instance of a class. ultimately, like the class is the blueprint of our specialized data structure, and the object is the actual structure itself. And the reason this matters is because I can create multiple objects of the same class. So let's say I wanted to run a couple different Kalman filters. Maybe one of them is using inflation, one of them is using localization, one of them is using neither. Well, I can create a Kalman filter object for like each one of those experiments, and each one can take different data values, different parameters. But the great thing about objects is they still use the same, like the methods are exactly the same, so you can keep reusing like the names of the functions for these different experiments. So I put a little example here, like object 1 might be like Kalman filter for experiment 1. Object 2 might be a Kalman filter for experiment 2, but I could run both of them using the Kalman filter not run. Maybe I jumped ahead of myself slightly here, but when we're working with classes and objects, we'll do something called dot indexing a lot. The dot indexing is both how you can access the data fields that are in your class, but it's also how you call the functions, the methods on an object. So the idea here is that, up above, I made an object to represent my Kalman filter for experiment 1. And if I want to get some sort of data property, I would take object 1, follow it by a dot, and then I put the name of the data property. So here in this example, we're doing object 1 dot label. That's returning the label of the for that object. And likewise, if I did object 2 dot label, it would return its label, which is different from object 1, even though we're using the same command. Very similarly, if you want to run a method on an object, you're going to do dot and then the method name. So if I want to actually run the Kalman filter for experiment 1, I would do dot run. Here's maybe kind of the first time we've seen some MATLAB code too. So just a note, when you run a function in MATLAB, the syntax is usually the function's name. So this would be like dot run. If the function doesn't take any inputs, that's it, you're good. Otherwise, you put the input arguments in parentheses. So option A, some parameter, option B, 5, whatever. That's what it would be. So I think another really important thing to know about Dash going into it is that we've really tried to focus on having comprehensive documentation for just everything in there. And so there's a couple ways to access this documentation. The first way is using help text, which is from the MATLAB console. So I'll show a little experiment or demonstration of this. So I go, make sure I actually have it. So one thing I'll note, I think everyone installed things using the Toolbox file, but if you did download the code from a zip file off of GitHub, then you'll need to add it to your MATLAB path so that MATLAB can actually find the code. That's what I just did there. You can, if you right click, you can see some tools to manage the path and go from there. So here I just added Dash onto my path so I can actually use it. Where was I? Oh, right. So we're going to show like how to access help from the console. The way to do this, pretty intuitive. Type in help, and then type in the name of whatever component in Dash you want help on. So I can do help filter. Hit enter, and it's going to give you a wall of text. I would recommend reading this from top to bottom. Typically, the layout for these is there will be a brief, one-line summary up at the top. Then we'll have a much more detailed summary between 2 lines of just like horizontal hyphens here. So here we're saying like, yeah, a lot of details about the Kalman filter, and we have some details about the algorithm. I've usually tried to include an outline for using a particular class or component, give a sense, of just which commands and what order to use them in. In the case of Kalman filter, talk about like how the algorithm works. We'll also talk about some of the features of the class. So like one thing in Dash is you can do inflation, do localization, something called blending. Some details about that. And then below that, I'll usually try to put in like what I think the key methods are going to be for anyone trying to use the class, and then a summary of all of the possible methods that you might want to use. If you're looking at help for a class, you also see these utility methods, which I would say just always ignore because you won't need to worry about using them. And if you have this wall of text and you want to clear it from your console, you can use MATLAB's CLC command for clear console. And that'll clear things for you. The other thing is you can like the help text isn't just limited to classes. It's also for every function that might be in those classes. So I might do like help common filter dot run. This will tell me how to actually use that common filter dot run command. Again, the kind of format's pretty similar. Here I usually try to do like the syntax for using the command, the description of how that syntax works. And like maybe if you have a modified syntax, here's the modified syntax, and this is like what the consequence will be. And then usually always try to put in the inputs and the outputs of what they are. So hear that. So that's kind of the help text. And again, you can access that by typing help and then whatever you want help with. But the other thing that we put into Dash is sort of an offline reference guide. A reference guide, which is sort of an offline website. And so if you want to access this, you're going to use the dash.doc command. So dash.doc. And this is going to take an input, which will be a string. In MATLAB, actually, before we even do this, let's say that in MATLAB, you can create strings using either single quotes or double quotes. So, filter, that's a string. I could also do filter, also a string.
Technically,
Yeah,
They're-
technically the
they're
single
not the
quote ones.
same.
Yeah, and I was just about to get
okay,
that.
all right.
Yeah. Technically, the single quote one is a character array. It's just a vector of characters. Whereas the double quote one is actually like an immutable string, as you might say in Python parlance. Like you can't change the double quote one. And why this matters is if you're trying to put a bunch of strings into a list, you're going to want to use the double quote strings. For example, I did single quotes, then string 1, and I did string 2. MATLAB's going to interpret that as just like a single vector of characters, and it's going to kind of combine them all. That's usually not what you want. Console again. Whereas if you do double quotes, string 1, here's string 2, those will be 2 independent strings. So useful to know. Okay, so backing up, we were at the dash.doc command. So that's going to be dash.doc. And then the input is going to be the name, again, of whatever you wanted help with. So common filter run, what have you. So I'll do common filter here. And what this is going to do is it's going to open up the reference guide. And here you can find pretty much everything that was in the console help text, but now it has hyperlinks, which I think is much more useful. We can see down here, like here are some of the methods that's in the common filter. Go to that run command. You can see here are the different syntaxes. If you want to see what this syntax is, you've got a link to it. If you want to know what this input is, like, okay, cool, that's what it is. This is really just designed to mimic the MATLAB help text. I think the reference guide is more useful, and I'll also note that as we continue to update Dash, we're going to try to add in like lots of examples for the kind of user-facing functions. The examples they won't be in the console help text, but they will be in the reference guide. So the reference guide is probably going to be more comprehensive overall. Yeah. One last note on syntax. In the documentation itself, you'll often see this like obj, and that's kind of the stand-in for an object. Like you need to apply a method to a specific object. I think in Python, this is typically written as like self.run. So if you're familiar with that syntax, this is how that would look. But yeah, so like output equals object.run. I actually want to run a common filter, I'm not gonna type common filter.run, I'm gonna type, object a.run or object. Cool. So here, we're gonna go ahead and move into our first coding session. I just wanted to give people a chance to, one, make sure that everything's installed correctly, but also just practice using dot indexing if you haven't before, and also practice using documentation. I think the steps should be pretty laid out here, but start by go ahead and just use the dash.version command, make sure things look right. You should have beta 4, should be the version. Try using the help command on dash.version and try using the dot command. Also a note for people who are here in person, I put sticky notes kind of around the room. As the workshop goes on, we're going to get into more and more complicated code. If you have a question about something, it's a pain to have to raise your hand while you're trying to type. So just feel free to stick one of those sticky notes on the edge of your computer, and one of us will come and try to help you with something. Oh, okay. Is anybody else not able to access Wi-Fi and would you like a thumb drive with files and download anything?
I don't know them already, but yeah.
Okay.
I can't patch this on my laptop, so I'm fine on my iPad. I'm gonna ask why.
Okay.
Anyway, yes.
Oh,
So EduRem, you guys aren't seeing it, it's not like strong enough here, is that the problem?
So you see it, but it's not back. There's one percent my login.
Yeah, no, it needs to be more of a persistent effort, like occasionally we can get in, but like like a little bit.
Yeah.
Like they didn't like that sort of. I didn't.
Yeah.
persistence
uh,
is up. That's-
Yeah, there's no.
Sometimes if you're, I don't know, EduRem can be like that.
I know, yeah, it's like that at C also.
Be a Mac problem. I don't have a problem and I use it, but I see.
All morning, I turned off my computer like 3 times, just clicking the Wi-Fi and eventually. Yes, allowed me to connect, there's just window to put your information in, wasn't popping up for me, it just said it couldn't connect. Just keep pressing it.
And also EduRem doesn't work.
What?
And the EduRem doesn't work.
It was, that wasn't working, but this person, the guest.
Yeah, you can handle that. Ronnie's fine.
I'm on it. But it knows.
This one's easy.
Yeah, this one.
Plus battery, and just like was it there?
Yeah, oh, it should sit there, yes.
Is everyone, was everyone able to run everything successfully, or is anybody able to run? Okay. Right,
Oh, yeah.
everyone on Zoom is good too?
Nowhere.
Also, here, I can give use your phone charger.
Cool.
Like an Apple.
If you're on Zoom and you have any issues, why don't we use the raise hand, commands, and yeah, we'll do that as the kind of signal for the day. Just, is there any way we could move the chat so that it doesn't hide this different people?
Yeah, well, if you're sharing screen, it's still
That's
gonna,
probably fine.
is that okay?
Yeah, that's fine.
Okay,
It'll just kind of be the gutter of the page.
yeah, it's mostly in the gutter, so we'll just put it there.
If you try exit the full screen mode, but then expand the window. I think the chat box will be merged into participant.
There's an email sent out to everyone yesterday.
I think this is okay, as long, because I think if they raise their hand, it should go, it should jump up and I want to see the chat in case anyone has a mess. This is okay, it's in the gutter, so for the most part.
I'll just make a note for everyone here too. If you you know, if you want to come back and find this website later, if you go to my GitHub. Oops, no, there's GitHub. If you go to my GitHub and look at the repositories, you'll see this Paleo DA Hackathon, October 2022. The repository there is like all the code used to build the website, but you'll find the hyperlink to the website down here. So you need to find it later. Cool. So I think we'll go ahead and move on to the next section here, which is our demo data sets. So yeah, so like I mentioned today, we're going to be using Dash to run a common filter assimilation. And kind of facilitate this, we've got 2 practice data sets for you to use here. These demos are derived from published assimilations. One of them is kind of based off of the LGM, last glacial maximum assimilation that Jess and Matt did. And the other one is based off of a tree ring assimilation I did for kind of a common era video. Feel free to work on both demos over the course of the day. Also feel free to work on just one. The common era assimilation I made like slightly more complex than the LGM assimilation. So that one will maybe be a touch harder to use, but I don't think it'll be too bad. And one thing I'll note is in these demo data sets, you'll see some files that end with a .grid extension. I mentioned that Dash had this like grid file component that you can use to build data catalogs. And so for today, I just went ahead and made all of the data catalogs in advance, and we'll look at them in just a second. But you should definitely check out the like gridfile class if you want to start implementing things on your own. I'll also note after this workshop, kind of in the next big upcoming Dash release, we're going to have a like expanded version of this workshop, which will have like how to use the gridfile class in it. So if you wait a few days, that might pop up online also. So yeah, quick description of the 2 demos then. Demo 1 is designed for the common era. So if you're interested in that, go for it. It uses a set of temperature sensitive tree ring records called the end-trend network to reconstruct surface temperatures over the last millennium. We're using climate model output from CESM, the last millennium ensemble. We'll be doing a pretty simple univariate linear forward model, but we're going to be training each forward model to our proxy records like optimal growing season. And each site has a different optimal growing season, so we can incorporate a little bit of proxy information there. But yeah, if you want to download the demo, follow the blue hyperlink, and I'm going to be calling this the end trend demo for the remainder of the workshop. If you download it, you'll see a couple files. Just up here. You'll see 5 files here. 3 of them are data files. You'll see these like really long named string like b.e11. A bunch of stuff, but 2 net CDF files. This is the climate model output. We also have this ntrend.mat file. This is the proxy record data set. And then we have 2 .grid files. ntrend.grid is the data catalog for the proxy records. And temperature CSM.grid is the data catalog for the climate model output. So the other demo, like I mentioned, is for the last glacial maximum. Here we're going to be using a set of UK 37 records to reconstruct sea surface temperatures, the LGM. Here we're using climate model output from 16 ICSM simulations and 89 UK 37 proxy records. We're going to be using Jess's baseline forward model. If you're assimilating UK 37 records in reality, there are some considerations of proxy seasonality that you need to take into account. We're sort of going to just neglect those today for the sake of simplicity. Although, if you're working ahead, feel free to try to incorporate proxy seasonality there.
And I can help you with that.
So again, yeah, follow the hyperlink with that demo. I'm going to call that the LGM demo. And then looking at the files that'll come with that. We've got 2 data files. We've got sst.mat, and these are this is the climate model output for the SSTs from the simulations, and they're time averaged over long stretches of time. And then UK37.mat, that is our proxy data set. And then we also have the 2 .grid data catalogs for those data sets. With that, we'll go ahead and move into the second open coding session. This is the first open coding session where we have some demos available. The way I've kind of set up the rest of these is I'll give you some steps and I'll show you the syntax for using commands. And then the solutions are here under the like ntrend demo or LGM demo pages. So you can click this, it will expand, and you can see, okay, this is how to use the commands, and like what the output you'd expect. I'd really encourage you to try to like just play around and experiment with the commands before looking at the solutions. But yeah, the solutions are definitely there, and you should use them as you want. But yeah, so in this first kind of coding, or I guess this is the second coding session, we're going to look at a few commands from that gridfile utility, just to kind of see what's in these data catalogs. And so the way that you can look at a, I call these data catalogs grid files. So you might hear me call them that from time to time. But if you want to look at one of these catalogs, the command you want is gridfile. You give it an input, which is a string, and that's the name of the grid file. And it should, if you do that, it should print out what it looks like in the MATLAB console. A note about MATLAB is if you put a semicolon at the end of a command, that will stop output from being printed to the console. So like, oh right, I have to actually give it a real file name. Ntrend. Like, cool, nothing happens because we put that semicolon there. That semicolon's pretty important as you write longer scripts, because otherwise MATLAB will just be spitting out every single thing you do into the console, and you don't want that. But here you can leave the semicolon off because we actually want to print into the console. And so, for example, I can look at that ntrend data catalog. And I can see like, okay, this is where that data catalog file is located. This data set has kind of 2 dimensions. It's got proxy sites over time. Got 54 proxy sites over 1262 time steps, which range from 750 CE to 2011 CE. We'll talk about these metadata columns later. This data set has a fill value, and you can see data sources here. That's telling us where the data in this data set is coming from. If I want to click on this, I can see where it's coming from, and it's that ntrend.mat file that we looked at earlier. And you can follow more hyperlinks, look at more details, and play around with this display. The other thing I want to talk about with gridfile is that each data catalog has metadata associated with it. If you are making one of these catalogs later, the metadata is really up to you. It's whatever you find useful. I really encourage you to use human readable values, meaningful metadata things. But we use this metadata at various times to like help design a state vector or to look for proxies in the ensemble. And so to return the metadata for the catalog, the command is gridfile.metadata. That is one of those object commands. So the way this might look is I would do, okay, this is my grid, like the gridfile command on its own will produce an object for your data catalog as an output. So I'm going to go back to that original gridfile command. This is for my ntrend data catalog. Cool, there's the object for that catalog. And now I could do object metadata. And this is going to return a metadata structure. You can see you know, this metadata has some information about the proxy sites, got some information about the time steps that are in this data set. It's also got some attributes. For those of you who are familiar with MATLAB, this is pretty much just a fancy struct. So the metadata command will produce a metadata object as its output. So we could do, I'm going to clear the console here. We could do metadata is create objects, you know. So what's going on in this command is we're taking our object, we're using the metadata method to return the metadata, and then the output is a metadata object. So we enter this command, there's the metadata object, and you can query any, you can query the metadata along the site dimension or along the time dimension with metadata attributes by doing the object and then dot indexing into that dimension's name. So I might do metadata object dot site. And that'll show me, okay, here's my proxy sites. Here, this first column is the ID of the proxy, second latitude, longitude, and this is the like optimal growing season. These are the months, so like July and August, or January through September, or what have you. Similarly, I might do in the metadata objects time. And here's all the time steps for the data set. And you can see it goes up till 2011. This is maybe a good time to talk about how you index in MATLAB. To do so, you're going to use parentheses. If I want to look at the first time step, I would do 1. MATLAB is 1 indexed, unlike Python, which is 0 indexed. So cool. You can create a range in MATLAB by doing like starting index, a colon, stopping index, 1 through 5. So if I wanted to look at the first 5 time steps, here I'm going to do my object time, like those are the first 5 time steps. If your array has multiple dimensions, so let's look back at the site metadata. We can see this one's actually a matrix. It's got some rows, some columns. You can index. You're going to separate the indexes for like the columns and the rows and whatever other dimensions using commas. So maybe I just want to look at the IDs for the first 5 sites. Do metadata sites. I would do, all right, I want the first 5 sites, 1 through 5 there, use a comma, and then I only want the metadata from the first column. I'm only interested in the IDs, so like the 1. And I would get some site IDs. It's come up throughout the day, but yeah, I think that's important to know for using that. Yeah, so I'm just going to give everyone some time. Go ahead and like look at those demo data sets. I showed you the end-trend one, but like look at the UK 37 data set, see what that data catalog, see what that looks like. Also check out the climate model output and get a sense for what that looks like. And actually, I can just walk people. Why don't we walk through them both so people kind of have an overview of what's going on. So we looked at the end-trend data set. Let's also look at the climate model output for the end-trend demo. So here I'm going to make my catalog for the CSM temperature. So here we can see this is, a latitude, longitude, spatial grid over time. We've got 144 longitude points, 96 latitude points. We've got a bunch of time steps at monthly resolution. You can see this coming from CSM1. I've set up the catalog so that this output is in degrees Celsius. One thing that gridfile will let you do is apply data transformations to data that's stored in other files. So for example, the actual raw temperature output is in Kelvins, but here we're doing a data transformation to degrees Celsius. Again, if you look at data sources, we'll see it's those 2 long output files is where this catalog will read in data from.
Just a clarification on the transform, that's going to be applied or that was already applied?
That's going to be applied. We try, these data catalogs are set up so that they do not alter the source files in any way. But one of the things in the catalog, if you're using them later, is there's a load command, which you can use to load, regardless of what file your data is in, and what format that file is in. And so when that load command is called, it's gonna search through these raw data files here. It's gonna find whatever data you requested. It's gonna pull that out. Then it's gonna apply this transform to it.
Jonathan, do you want to, because we're not gonna show people how to make grid files, right?
That's right.
So, but maybe you could demo out with this example, like just kind of walk through how you did set it up. I mean, and then they can, do you want to?
I would rather not
Open
that right now.
Okay,
Just for time.
okay,
purposes.
all right, if we have time to go
Yeah.
back to that.
Well, okay.
I mean, you have a straight up net CDF there, so.
Yeah. Okay. I'll give a quick one. I'm gonna do this kind of fast. We're not gonna spend time on it, but just to give a sense of what the workflow looks like.
Yeah.
When you create one of these data catalogs, what it's doing is it's kind of managing an abstract n-dimensional grid. And that grid is tied to various metadata values, and you'll go along and say, hey, this portion of the grid, that's the data in this file. This portion of the grid, that's the data from that other file. So the way this workflow would look like is, let's say I want to make a file for my net CDF one here. I want some latitude metadata, some longitude metadata, I want some time metadata. You can use whatever you want for those metadata. They just need to have one row per the length of the dimension.
If I could back up 1 second, just explain what gridfile is doing, so you need to have your model prior, right? So let's say you go and you download that file that's there, and that is tref height, and that is sort of a typical file name you might find from the community or system, that looks something like that, right? So that's your air temperature, and you downloaded that, and so now you have it on your computer, and that's what you want to use, your model prior. So what gridfile allows you to do is access all that information in the netcdf file without actually having to reformat it. And it's just kind of a map.
Yeah, you don't. Yeah, a map is a great.
It's a map for let me tell you what you need to open in there to get the data in the format that you need it is. So it's a translator from the netcdf into being able to now do all the data.
A map library is like.
Yeah. And there's a lot of options for setting up a grid file, so we didn't want to get dragged down on that. But I think it's important to maybe run through how would you just do, because it's just one variable, how would you just sort of set it up? Download that netcdf and now what, right?
Yeah, okay, so we'll totally do that now. The other thing I'll comment on is look for the updated dash version next week, and that will also have a tutorial on making grid files. But the basic workflow is we're going to start out by saying, okay, we need to define what the scope of our data set is. We're going to do that using some metadata values that are, the dimensions of our data set. So in the case of this example here, we're going to get the name of the netcdf file. This netcdf file, we can use the ncdisp command to see what's in the file. Let's try this. When I was sitting on stuff. There we go. Yeah, ncdisp.
If you want to do this, you can always do this in a open script.
Yeah.
And you want to say what you're doing. You can just hit
Yeah.
script.
That would be good to do. Let's do that. So
And then you
here.
can say this in case I'll look at it.
It's a grid file demo. The first thing we're going to do is get the name of a file here.
Is there any way to increase the font size?
There is, I don't know how. Oh, hey, yeah, that was easy. Great. Thank you.
Yeah.
How's that? Bigger still? Okay. Cool.
Yes.
So comments in MATLAB or with what is this percent sign? So we might want to look in the file.
Okay, where did you get that file?
Just copy paste.
I copy pasted it. Yeah. You know, and so this will display things in constant. If you look in here, there's a lot of metadata for this file, but two that I'd like to highlight are that this file already has latitude and longitude data. And I think that's pretty useful. So I'm just going to use the metadata that was provided with this file originally. So now we're gonna start getting some metadata. So I'll do lat. MATLAB has a command called ncread, where you input the file name and then the variable that you want to read out. So here's my file, and I want the lat variable. If I actually do that, I'm going to run this in the console now. If you see me like double click, like highlight and then right click, that's what I'm doing. You know, so we do that and we see, okay, this is that latitude that's in there. Cool, that looks super useful. I'd like to use that. So we're just going to kind of save that as a variable here. Similarly, I like the longitude data that's in there. So I'll use that also.
So NCB, by the way, is the way that NCB is the magic operator.
The magic
MATLAB
command that
reads
gridfile
things
is
together.
wrapping to,
Yeah.
but it will also do a lot of other things.
Jonathan, can you show us the rest of the text in the file, because I don't follow this.
Oh, yeah, okay. So
In fact, that is not.
is this good?
Yeah.
Cool. So another thing that this file has is time metadata, but I personally find it hard to interpret as a human.
Yeah, this is really typical of
Here we
the
go.
output from C and CSM. The
Yeah.
time is pumpy stuff.
So this time metadata is in days since 1850. And we want to take a look at that really quick in the console.
Even worse than the years.
It's hard to know what this time actually means. So
I'm sorry.
So here we're reading it, we're using the ncread commands to read it from the file. We're going to read out the time variable.
Oh, just like.
Yeah.
Oh, yeah.
So when I really want to encourage people, when you're using Dash, like please try to use like human readable metadata. It's going to make your code like reusable for you. It'll make it so you can attach it to a publication, know what you did. That's important. So I'm going to kind of, I know the time span that this data set goes through. It's monthly. It goes from 850 to 2005. So I'm going to, write that time metadata in a format that I like a little bit better. MATLAB has a time format called datetime. I really like it because it lets you sort things by year, it lets you sort things by month, by day. And so I'm going to create that time metadata to date time. Here the inputs are year, month, day. So 850, starting in January, just center of each month. And I previously mentioned you can use a colon to make like an array of integers, but you can also use it to make an array of like date time events. So here we're going to make an array of date times. They're going to be spaced out by 1 calendar month is the spacing. And then it will end in 2005 in December, just middle of the month. So if you run this command, now we have this time variable, which is long, but you can see like there is all the different time steps that's going to be in our model output. So we're going to clear the constant. So to make our grid file, we're going to define, we're gonna create a metadata object. We'll use this metadata object to like define the scope of the file.
Jonathan, that time is not the same size as the file.
Typo here. Oh, okay, sorry, yeah, I should clear up.
Okay, yeah.
Yeah, this time is spanning our entire data set, and our entire data set is spread over 2 different files.
Sorry, yes,
Yeah,
sorry.
yeah.
If you do want to hard code this, maybe I'll try and draw something easier. There are internal functions that allow MATLAB to say, okay, those weird numbers are days, and they're days since some baseline date.
Yeah.
So I can pull that out. So you're less into the hard coding, all the.
Yeah, you could ask it to read it out.
I'll try and help it.
So, yeah, I'm not gonna go into too many details on these metadata objects, but you use the grid metadata command to create one. The syntax here is, the inputs are the name of the dimension, that dimension's metadata. The name of another dimension, that dimension's metadata. Dash has some supported dimensions, and you must use those dimension names, although you can alter Dash to include other dimensions. To see the dimension names, type in dimensions. You can see those are the names of the dimensions that are kind of built in. Longitude, latitude, lev is for like height or depths in the ocean. That's nice for a 3D spatial grid, but sometimes we have like just randomly distributed like proxy sites, or I'll talk about tripolar grids later, but if you have kind of, sites that are not on a rectilinear grid, you can use a site spatial dimension. We have time, we have run for like different ensemble members in group of model runs. We also have a bar dimension for like different climate variables. And you can edit Dash to include other variables, or if you don't like these names, maybe you want to use longitude instead of long, you can change Dash to do that. I'm just going to stick with these for today. So I'm going to clear my console. Actually, here, put this in our script. Display metadata dimension names. Okay. So we're going to create a metadata object using this lat, long, and time metadata. So find scope of dataset. So here's my metadata object. I'm just going to call it meta. Grid metadata is the command, and then we're going to do dimension name, followed by what the metadata is. Dimension name again, followed by what its metadata is. Yeah. Now, I think I mentioned earlier that you need to have one row of metadata per like length of dimension. You can have as many columns as you like, you gotta have one row. Currently, this time metadata here it's a row vector. So this is the way that Dash will interpret this will be as a single point in time with just like a ton of metadata values. So you see if I run this command as is, we're going to get a little warning. I'm going to clear the console. Oops. It'll give me a warning. Oh, forgot to actually run this code. So let me run this code. Cool. Running this code. And you can see when that went by, it spit out a warning where it's like, hey, by the way, this is a row vector. Are you sure you want your time dimension to have a single element? Probably not. So in MATLAB, you can flip a row vector into a column vector, or take the transpose of a matrix by doing a single apostrophe. So we do this now. Go to the console again. Run this line. No more warning. Now that we've run this, this is that metadata object that we got when we did gridfile.metadata earlier. Yes.
Can you explain again why, or what you did with the error or the word?
Yes. When I did this line right here, this created a row vector of like dates. MATLAB, I should maybe say, if you're coming from Python, Python has true vectors where they just have a length, and that's it. MATLAB does not have true vectors. It will have, a matrix with a single row or a matrix with a single column. So when I created this, I created a matrix with a single row, but really what I wanted was a matrix with a single column. And you can take the transpose of the matrix in MATLAB by doing an apostrophe. So down here, I added an apostrophe and that flipped the time from a row to one.
In this spirit of visualization, if there's any question down in the workspace, you can just double. click.
Yeah. You can look down here, you can see that time has one row and a lot of columns. But if I do time equals time apostrophe, you can see time flips and now it's got a bunch of rows. Okay. So you define the scope of your data sets. Now you're going to create a data catalog file. The command here is gridfile.new. Input is what you want the name of your file to be, and then the metadata that defines the scope of that file. So create, maybe we'll say initialize a grid file. So the output of this will be an object that you can use to interact with that catalog. Gridfile.new. I'm going to call this demo file. And here's the metadata that defines the scope of that file. So if I run this command, see that over here in my workspace, it created that demo file. You look in the console, we can say, hey, okay, here's our data catalog. This is this is the metadata defining it. We also know that it has no data sources. I want to emphasize these catalogs, they're strictly catalogs. There's no data stored in them. You're not going to be saving and duplicating data, you're creating them. All they know how to do is read data out of another file. Currently, this file has no data sources associated with it. We can try to load data out of it using the load command. And it'll totally work, but you can see the grid is completely empty. MATLAB uses this value NaN, not a number, to represent missing data. So still going. I'm gonna stop that. So it's completely empty. So the next thing we need to do then, I'm gonna put it.
This is just going, especially because it emptied the dimensions of that one.
No, it's not. So the metadata defining the scope of our grid file is there. That's the thing that's stored in the file. The grid file stores metadata and then like the locations of the files, along with a few other little miscellaneous things.
What was the dimension of all those names?
So that would have been 144 by 96 by 13 by 17. Yeah, but if you want to look at grid metadata lat, like boom, there's our latitude metadata, or grid metadata. Oh, I should mention, if you press up in the console, that'll give you can scroll up through commands. So if you see a command pop up really fast, it's probably what I did. So you can do grid.metadata.time. You can see the time steps for this data set. Anyway, so you've created your grid file, and the last thing you need to do is tell it like where the actual data files are. The command for this is gridfile.add. Add some data sources. I'm going to type out some stuff here, then I'll explain what's going on. One of the things you need as input is like what the actual order of the dimensions are in the file. So I know in these netcdf files, you can use the ncdisp command to look in the file, and you see that the variable in there is organized as longitude by latitude by time.
So which command do you use?
That would be the ncdisp command that we did earlier, where I would go, I guess, file, maybe so the name of the variable in here is t-ret. You can see it's longitude, latitude by time. The other thing we need is, if you're using a netcdf file, you need to know what the name of the variable is. A bunch of variables in the netcdf file, and the catalog needs to know which one you want. So do variable name. Correct. We're gonna what type of file this is. This is a net CDF file. We'll know what command to use to read data out of. And the last thing we need to say is what portion of this data catalog is occupied by this file. What are we on time? Oh, we're still pretty good. Okay, cool. So we can use that metadata object for meta. There's a command called metadata.index, and that will allow you to like select certain reduce the metadata to a certain set of indices along a particular dimension. So, file 1 metadata spans the first 12,000 time steps. 5,000. And the second file is the other time steps. If I were to run this command, see what it looks like. Let's look at file 1 metadata console. You can see like, okay, cool, now time is these 12,000 time steps. If we look at file 1 metadata.time, we can see that it ends in 1849. When you look over here, you can see from the file name, that's when that file ends. So now we're going to add them to the grid file. We're going to do grid.add. That CDF file. I'm going to back up real quick because the two different files have different names. So instead of using file, let's do file 1. File 2. File 2. We're going to add file 1. The variable name is the third input. The dimension order is the fourth input. And the metadata defining the scope of that file is the fifth input. I'll note that Dash has like a ton of error checking built into it, so if things mismatch, it won't let you. Like if you give it incorrect metadata, it won't let you do it. I might, let's say I accidentally gave it files 2's metadata. Find my file names. Sure. Yep. If I try to do add file 1 using file 2's metadata, and I forgot to release. Let's do all this. It'd be like, hey, the number of metadata rows in the file doesn't match the length of the dimension in this big long file here. So if we fix it, we can run this command. Let's look at, so when we run this command, it's going to update this demo file.grid over here. We can look at the, I'm going to clear the console. We can look at the grid file object and we'll see, hey, now it has a data source. I'm going to look at that data source. You can see it's that first file. And now if we did drop grid.load, the first bunch of values are going to be real numbers, and there'll be a ton of nans at the end because of the second file. So yeah, there go a bunch of numbers. As they go by, you can see they're probably in Kelvin. That's enough of that.
So also if you're on a Mac, the shortcut for running the line is highlight it, press FN shift F7.
Okay.
That's the way to run a line.
Changes to describe the data sources up here. Changes to add data source files. Yeah, file 2. Variable name. file to metadata. We run that line, we've added our second file. And there's, now we have a complete grid file. And I'm not gonna go into the data transformations. I think we'll save that for another time, but yeah, that's kind of the process for building a grid file, and yeah, that would probably be useful.
Hey, Jonathan, is there a way we could call in CGS to see the variables? Because the default in CGS is to show the global attribute.
Yeah, that's a good point. So we could do NC disk. And then the second input is the a specific variable's name. So actually,
So is there a way to see the list of variables?
I don't know.
Yeah,
Like,
you
you
can
tell
see
me.
Like if you just click on the answer, right, and you can actually sort.
I always just scroll through the console. If someone knows a better way to do this, I would. Yeah.
Wait, what did you just type there?
So that was the NC disk commands where I gave it the file name of an NCDF file.
Just the file and no.
Yeah, but if you want to look at a specific variable, you do T.
Right.
Like this.
Oh, I guess I use NC info.
Okay,
And then
yeah,
it
that's
puts-
useful too.
Then it puts it into your workspace, and then you can actually fully explore all the different.
Okay, so just to put that on screen then.
That's, yeah.
Okay.
Yeah, I think that's.
You could do info equals NC info
Yeah, I think it's too. For that.
folder.
Yeah.
Sure. Oh, yeah, you got the variables down here. Yeah, you can play around with that. So yeah, probably, I guess, yeah, thanks for that suggestion. Yes, I would suggest save that, and if you're trying to build a grid file later, that's kind of the standard workflow. Yes, Dave?
So if you were to, is there a way to add multiple variables to this and also give you variables like the depth dimension?
Yes, so if you'll recall, when we were looking at the metadata dimensions, there's this lev one.
Okay, cool.
I took the name lev, I guess, from the atmosphere model, but it's meant to represent like a heights dimension. It could be ocean depth, it could be atmospheric levels, whatever you prefer.
That worked good.
Yeah, and then also, yeah. Also this bar dimension you can use to do different variables, so long as they're on, the same spatial grid. If they're on a different spatial grid, you'll want a separate file.
Yeah, I find it just for my own sanity, you could put everything in one grid file, but I often make a separate one for each variable. So if I'm doing like temperature and then you said, and then something else,
Yeah.
I like to separate them in grid files, just.
I think we do that too.
Yeah,
I think it makes building state vectors a little easier to kind of read like what variables actually be. We haven't kind of got to the state vector building code, but I'm with Jess. If you have like 70,000 variables, okay, maybe you don't want 70,000 catalogs, but like I don't know. I feel like I'm usually working with like 1 to 5 variables, and I'm fine having like 5 data catalogs.
Yeah, no, I just want to make sure you put multiple together to take that.
Yep. Cool.
Might be a good time to take.
Yeah, I was gonna say, let's take a 5-minute break, and then we'll jump into building state vectors.
Actually, we can share those first 30 lines of code.
Yeah. Grid file. I'll call this build.
Yeah.
Grid.
All right, well, we're gonna take a short break and then,
Oh,
Yeah, it's like I had.
I can drop this in the super chat for people. Oh, and we have some.
Yeah. let's-
Yeah. It's Boston TV.
So for anyone on Zoom, I just dropped the that demo code in there. I will also.
Yeah.
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 Beautiful. That's it.
That would be the script. Yeah, so Matt raises a yeah, so the third commit. All right, so I'll grab everyone's attention real quick.
Formula.
Yeah, okay, come back. Yeah, take the third input true. And the third input to do is whether you're allowed to put right file, just like that, yeah, so.
Yeah, okay, so yeah, that's better, I was getting. So if you.
So if you look at, so two, one, I would say this is a good time to look at the dash helps see what all the gridfile that you can do. Yeah, so the third input is whether you're allowed to write. File, so if you make third input true, it's good, and I'll come back.
Right, is this for grid file?
Yeah.
Okay. Yeah, yeah.
And version 4 is very slick. Very quick.
It's, yeah.
I think I slipped up version 2.
I don't know.
Too.
Let's try it on this. So like on Windows, it's a couple to see the task manager. I mean, sometimes I like to do this. Your computer is just like it's got a ton of that. Yeah. Maybe try closing a bunch of stuff, and maybe you can reopen tabs, but.
Yeah,
for sure.
yeah, no, yes, it's fine. That's fine. Yeah.
Yes. So you repeat this is the, yeah. Yes.
It's fine, because quick metadata is just a function in that, it's not native to MATLAB.
Right, that's a thing.
So for the 7 variables that you listed, we can change that.
Yeah, I'll also touch on that. People are still
I mean,
on,
it's
right?
in the,
Yeah.
yes, X-rays made a lot
I'll
of
be right
progress, but like, it is, yeah, a lot of the. Projects on it. So it'll give you like seconds, but if I want. I guess. Yeah. Maybe that's a lot of zero. Maybe that's not. Like, version 4 is like. It's not as easy as. It's like, or it's absolutely voter calls. So like.
This is pretty similar, but yeah.
Yeah, but all like, they're like the, so that makes you slightly different. So
Oh,
there's like
okay.
a really steep.
That's right.
Modifying your code from the old syntax to the new one, but I found that it's really like. It's actually more intuitive once you unlearn the old syntax.
Yeah. This is the ultimate, big user test. It's done and said before we submit the GNG paper.
You should do a workshop at AGU or something.
About this.
Yeah, I love, they have these tutorials.
Yeah.
It's pretty polished.
Good to have a chance.
Really?
All of us. They've already figured it out. Cause even beans and rice. And
I know.
Oh,
If the one that isn't.
Or just.
yeah, open the rice book. We're getting more, so
I
please.
wasn't expecting
Not
that.
as your new one.
Yeah.
Cool.
Okay.
You're like,
No,
oh,
it's good.
Yeah, it'll be small and fast.
How you guys? like the script.
One problem I was saying is I use tamale like often because like one tamale. Day. It's like throw it in the bag. Consequence though, I'm almost like out in quality. Some flavors.
Evan, what, the dimensions?
Marcus is confused about this.
Yeah, you-
That's a dimension.
Oh, okay. I'll even see.
Yeah.
He's saying that we're in far out, it's,
It was insane,
it outputs to.
but I definitely did mean to know, but.
They're usually long last.
How about it?
Last
Oh, yeah,
time, right?
Then I would order 3 hours. Oh, this is why I know.
Well, I don't know, I mean, if you could, so I've got a.
Oh, there's a guy.
I know it's usually long last, just
Right.
fine. Yeah. Maybe not all.
Hey, may I just chime in here and explain what I mean? So if you do an NC dump on the data, like I haven't actually looked at the files you have, but I have access to the same files. I assume it's the same thing. And the climate, all the climate models are saving data as time lat long. But when you read it into MATLAB, it seems to transpose the matrix. So
Yeah.
I mean, it's more a curiosity than anything else, but it's kind of important to know all these things, obviously.
Alright.
And it's the same if you read it into Python, then the dimension is time lat long.
Yeah, Marcus, so if you do the NC disk, it says, time, sorry, it says, all that time. If you look in Monopoly, it says time long lat, but if you just read it straight into that lab, you do get 144 by maybe 12,000, so. Know what to make of that.
Already on my start.
It sounds like MATLAB is shifting dimensions somehow. That's the case, an output of it.
There it is.
That's weird. It just feels that was the way the files are. Yeah.
Of course. If the boundary is
Okay,
covered.
Oh, yeah, but all the ones.
okay.
I mean, I don't care if you
I'll
was
just
like
leave it
copying
in.
over here,
There
like.
should be one. There's
There's
one
one
up
up here.
here,
Okay.
and a floor, there's a floor. You wanna stay on?
There.
Yeah,
I'm not.
Mostly back.
No, it's saying.
I'm gonna address like 1 or 2 comments from people and hopefully they'll be back then. Okay, so one thing I wanted to mention here is that most of the commands in Dash have like a number of options they can also provide with them. Most of the stuff I'm showing you today is kind of using the base syntaxes, so there's often like more features that we won't discuss. One I want to point out is that let's look at gridfile.new. Especially when you're building a grid files kind of for the first time, it's nice to experiment and kind of rebuild them a few times. And so you can use the third input to indicate that gridfile.new is allowed to overwrite an existing file. So if we make this one third input true, then I think some of you mentioned having like getting an error where it's like the file already exists, and so this will let it overwrite the existing file. And again, just kind of as a reminder, if you want to see all the options for like commands, dash.doc is a great way to go. If we go there, we can see, oh, here are the 2 syntaxes. We can do just the file name and the metadata, or we can do the file name, metadata, and this override function. Jumping down to that syntax, this override variable, and see that it's scalar logical. That indicates whether you're allowed to override or not. The other thing a few people asked about was the dimensions that are supported in Dash. So if you want to play around with these, you can do edit, grid metadata. This will open up the grid metadata class. But I've included a section here up at the top. I'd like to add new dimensions. Add them in right there. Likewise, I think I said here, you can rename these dimensions. Don't delete them, don't change their order, but you know, I could change this to like longitude if I wanted, if I find that more informative. Yeah. Cool. All right, so I think we're gonna go ahead on to building state vector. Just a warning in advance, this is the section that's probably gonna you're gonna have the most new concepts here. So yeah, a little bit of a learning curve, but once you have these concepts, you can build just about any state vector, so they're worth knowing. So go ahead and jump right. So yeah, here we're going to use, before we were just using the gridfile class, now we're going to be using the state vector class. And as the name suggests, you can use this to design and build state vector ensembles. So this class creates state vector objects. And what these objects are is that they're a design template. And they say, this is how I want my ensemble to look when I decide to build it. I think a really important point is you're not going to actually build the ensemble from values in the data files until the very end. And all these steps, we're not manipulating a bunch of data. We're instead saying like, hey, I want my state vector to have a temperature variable and a sea surface salinity variable. And I want it to be in the northern hemisphere, but I don't need the whole global field, like things like that. Yeah, so almost all these commands we're working with the design template and then very end. Right, so we talked about state vectors earlier. I think we'll do like a little bit of a deeper dive just to get a sense of what should be in your state vector. And so ultimately there's two types of variables that should be in there. You want to have your reconstruction targets and also any climate variables that you need to run your proxy forward models. And in some cases, you know, a reconstruction target might also be what we're using to run the forward model. You see this a lot with like linear forward models. So, you know, Venn diagram there, you can have overlap. But whatever your application is, your state vector can include data from a variety of different climate variables at different spatial and temporal resolutions. You can have variables from different data catalogs. You might have something from an atmospheric model, but also from like an ocean model component. Also possibly a kind of different time intervals. So what I've kind of tried to illustrate here is just like an example of a state vector. You know, you might have a gridded temperature field that's on some sort of monthly resolution. Maybe this is like the summer mean of that temperature. But you could also have the like annual global mean temperature index also in the state vector. For the purposes of Dash, you know, I would describe those as kind of two. They're both temperature, yes, but I'm going to call them two separate state vector variables because you know, one's an index, one's a spatial field. Yeah, it's up to you. Yeah, and I might have another variable representing precipitation. Yeah, so as we mentioned, we're really focusing on ensemble DA methods here. And I think I mentioned this earlier in the primer, but when we build that ensemble, we're often selecting data from different time steps or you know, a stationary offline prior, or from different climate model runs, or you know, an evolving offline prior or another application. Or from different climate models, which is something I think we touched on at the end of yesterday's discussions. But so like, just kind of sketching out what this might actually look like then is, you know, here's my little sample ensemble. Ensemble member 1 is selected from year 1 and run 1. Ensemble member 2 is a different time point in the same run, whereas like this ensemble member over here might also be from year one, but it's from the second climate model run, and so it's, you know, it's a different set of data. So now I really want to like give a strict definition for what I'm going to call a state vector variable for the remainder of this workshop. When we're building when we're building a state vector in Dash, we're going to be using data that's organized in those grid file data catalogs. And that's just like pretty open-ended with how you can build a state vector. So our definition for a state vector variable is just some subset of data from a grid file. You can have multiple variables derived from the same grid file. So for example, I might have this monthly temperature field, and then also a temperature index that I also derived from that temperature field. And each of these variables is going to be a contiguous block of the state vector. You can also have variables from different data catalogs in the same state vector. That kind of goes to Dan's point maybe about adding multiple variables in there. Yeah, and I wanted to emphasize that a state vector variable is not necessarily a climate variable or a single climate variable. If you had a data catalog that had multiple climate variables in there, you could turn that into a single, block of the state vector that was those multiple climate variables in succession. And I would still call that a single state vector variable, although for practical purposes, you should probably separate these when you design your state vector.
Wait, so in your example, though, you have both precipitation and temperature,
Yes.
but you're saying you should separate them? Yes, what are we separating?
Okay.
Sorry, did I just ask?
No.
Yeah.
Let's say. Let's say I had a data catalog and it was like temperature. And then there's like a precipitation grid.
Right.
And then probably sea surface salinity wouldn't be in here, but I'm gonna write it anyways. Yeah. So you could make a data catalog that had all like 3 of these variables in it, right?
Right.
And if you're creating a state vector variable, it's just saying it's some subset of the data in this catalog. So I could create a state vector variable that would, somebody give me another atmospheric variable.
Humidity, 500 milligrams.
Okay, 500. I could create a state vector variable that I might call like CAM, or the atmosphere, right? Where it's, here's my like atmosphere state vector variable, and it would be like the temperature grid, and then also the precipitation grid, and also 500 millibar height data. It's
So,
you all can
like
see it.
what you just did there with temperature.
Yeah, totally like that. What I'm saying is, rather than, it depends on your application. Rather than creating a like atmosphere variable, I think it's more readable for other people to be like, I'm going to add in the temperature variable, and then I'm also going to add in the precipitation variable, and like just give like identify them by their climate variable names. I guess is what I'm saying.
Okay, but you can still put them all in one state vector.
Absolutely.
You just need to metadata. Identify.
Yeah. And to Jess's point, like we said, I think both Jess and I don't know how you do it, Emily, but we tend to make a separate data catalog for different climate variables, and none of this will really, like, you won't have multiple variables in the same catalog, so this like really be.
I put everything in the same place.
Okay, well, never mind. So cool, you can do it however you like. It's flexible.
Yeah, I put the each variable in its own grid file, but then for the when you build the ensemble you're actually gonna work on, it ends up being everything is together. So,
Yeah.
So and one thing I was gonna add about, because Emily was just mentioning about global mean temperature is, yeah, so you can ahead of time, you can take the global mean temperature and just put it in your state vector. That's all you're interested in, you don't have to put anything else in there.
Yeah.
Although, as you know, keep in mind that for your PSMs, you may need some variables for your PSMs. But one thing I want to just caution about that is that So if you have temperature and then you go mean temperature. And if you have your fully gridded temperature and then you update that and you calculate TMST after the fact, it will be the same as updating T mean only if you're not localized. So if you apply localization, I highly recommend you do not add mean temperature to the state vector to be the update is not identical, and that's
Yes.
because the localization, remember, affects the variance matrix, so it won't update it the same. So let's cover that. But if you have no localization, it is the same.
Another comment too is, if you do calculate it both ways, you can always compare the two. They look drastically different. Might be something up, like you might have a really, really narrow localization radius, so like actually most of the spatial field's not being updated. Probably not good, so that could be a check. Yeah. Okay, so we're gonna kind of introduce our first new concepts here. So in Dash, I'm often going to refer to things as state dimensions or ensemble dimensions. So what this means, if something is an ensemble dimension, it's one of the dimensions that we're going to use to select different ensemble members. So if I'm selecting ensemble members from different points in time, then time is an ensemble dimension. If I'm selecting from different climate model runs, then run is an ensemble dimension. Kind of trying to show in this figure here is that metadata for the ensemble dimensions are going to be unique for each ensemble member. Like this is year 1 from run 1. This is year 19 from 1. This is year 1 from run 2.
Because if you have identical columns, that's gonna,
Then you've just duplicated some data.
it also makes your covariance matrix, poor.
And Dash won't let you like. Actually, I'm not gonna say that. You can if you want to. It will, by default, it will not let you duplicate stuff, but you can request that you want it duplicated or something. So by contrast, a state dimension is any of our data dimensions that are not ensemble dimensions. So this is typically our spatial grid. Like the latitude, longitude points we looked at earlier. And I think what's important to note here is that each row of the state vector is going to have a unique metadata coordinate for those dimensions. Like the first row is always whatever this latitude, longitude coordinate is. The second row is always the data from whatever was at this small grid point, and so on.
But if you've got like both temperature and precipitation, you would have separate. It would
Yeah,
like
so
both
what you
lines.
get then is you have like flat, oops, that's. You'd end up with like. Here's the temperature part. Here's the precipitation part. Here's my state vector. I'd end up with like flat, 1, 1. Flat, 1.
Right, so you repeat all those like.
And down here, I have flat on 1 again. Flat on 2. And so. Yeah, and a common breakdown here is that kind of these spatial dimensions, optionally variable dimension, are our state dimensions. Time and run are often our ensemble dimensions, but it's not always the case. It's not a strict requirement, so yeah, keep that in mind for whatever your application is. The kind of other new idea I want to introduce here is something that I'm calling a sequence. And so this is when I want my state vector to include like data from successive points in time. So one example might be like, I want the temperature field from January, I want the temperature field from February, and I want the temperature field from March. So this is what I'm calling the sequence. And what's important here is that time is usually an ensemble dimension. We think of it as, going back to this figure here, back up above, we think of time metadata going across the columns of the ensemble. But when we have a sequence, the time also has some metadata down the rows of the ensemble as well. So for example, I'll have the whole spatial field in June, I'll have the whole spatial field in July, the whole spatial field in August. the main takeaway point I want to have right now. But ultimately, like if you want to put a sequence into your state vector, you're also going to need to indicate like, hey, this first block of values is from June, this first block is from July. So you want to add an additional bit of metadata there. We'll look at the commands for that in a second. Does anyone have questions on sequences or like, state and ensemble?
The sequence is just like what you have up there, except it's instead of temperature and precipitation, it'd be like July and like August.
Yeah, so I might, I can still have both, you know, I might have like June, temperature in July, precipitation in June, precipitation in July, you know, then I would have multiple variables and all of them would have sequences. Alternatively, like again, this is, you're gonna be able to build things flexibly, so you know, maybe you want temperature in June, July, and August, and you only want precipitation in June, that's fine, you can do that too.
So you would want to do this if you have a seasonal PSN or if you're trying to reconstruct.
Quick question.
Yes.
So for the state vector, can we still be able to index each grid cells with the metadata, or it's okay?
And
It's
we'll,
not just turned to be like 1 to whatever.
no, there's a lot of, there's another metadata object that comes with Dash. We'll look at it later, it's called ensemble metadata, but it allows you to query like, what's in this row? Or like, please return me the rows that are for this variable, or you know, the row for this latitude and longitude points that's closest to my proxy data, or well, I promise we'll look at that more there.
And there's a regrid option too.
Yeah, there's also a regrid command which will, you know, take a state vector ensemble and reshape it back into the variables like latitude, longitude, time, spatial.
The reason I'm asking is I used to do state vectors for my class project in Python, and I haven't really know how to put all the metadata to
Yeah. Yeah, it's a pain.
to come with the grid. So I only have to remember how I reshape my original lat long,
Right.
and then when we have to reshape it back, it's had to be a certain direction.
Yeah, hopefully, yeah, that's set up so that you don't need to know like how it's built. It'll give you commands to like find what you're looking for and regrid out with them.
Yeah, this is the major.
Yeah,
This is one of the major.
meat and potatoes,
Use this
yeah.
software package is that it's very organized, it remembers where everything is, and then therefore preventing you from making a potentially bad mistake.
Yeah.
As you're moving things and reshaping.
So the other thing I want to talk about is a few different types of indices that we'll be using. Some of the commands in state vector take indices as an input. For example, maybe you're only interested in the northern hemisphere. So you only need your state vector to include temperature from latitudes above the equator. You can give it some indices to say, hey, that temperature variable, like that latitude dimension, just give me the upper half of data elements along that dimension. I want to just like as a general recommendation though, like indices are not very like human friendly, they're not very human readable. So if you want to get like a set of indices, for the northern hemisphere, I would recommend doing so using your grid file metadata. So as an example, earlier we looked at like metadata. I could look at the latitude here. Meta.lat. Okay, I could see like here's a bunch of latitude points. And if I wanted, I could do like northern hemisphere is equal to 49 to 96. That's valid. If you do meta.lat of 49 to 96, like cool, those are the right values. But like 49 to 96 doesn't mean anything to me as a person. So what I would instead recommend you do is if you're going to get indices for something, do like the northern hemisphere is meta.lat where it's greater than 0. that'll give you a whole set of indices. You don't actually need to look at these indices. You know, they're well represented by just Northern Hemisphere. That makes sense. And the ones here, because MATLAB does logical indexing when it can, you know, I can use find to convert them to linear indices, and we'll see it's just the values 49 indices. Yeah, so as a general rule of thumb, please try to use metadata to like index your stuff and make your code more readable. All right, so different types of indices. State indices are the elements along a state vector dimension that you should include in the state vector. So for example, and I should say all of these indices are defined on the scale of individual state vector variables. So like a state index. This might be those Northern Hemisphere indices saying like, hey, I only need data from the upper half of the globe. But maybe I want the Northern Hemisphere for temperature and the whole globe for precipitation. That's totally fine. You would just give them different sets of state indices, and each variable would implement whatever it needs. Reference indices are going to be how we select different ensemble members. And yeah, so essentially these are the elements along an ensemble dimension that we use, that Dash will use to select the ensemble members. So like we can say like maybe this is the time dimension, and each of these dots is like a monthly time step. And maybe we want to select ensemble members specifically from the month of January. So we're doing like a January seasonal reconstruction. Then the reference indices in this case would be pointing to like, I think these are separated by like 12 dots. I'm not going to count it. If they're not 12, pretend they're 12, you know. So like one reference index would be pointing to this 1st January, another reference index would be pointing to the 2nd January, and so on. In this case, Dash wouldn't select ensemble members for February, March, April, January's. By contrast, you could put a reference index at every single one of those months, and then anything could go in the state vector. It's, you know, whatever your application is.
So what were your ensembles divided up into before? Because you didn't already have every single month as a separate ensemble member, right? Like, so is this like creating ensemble members out of previous larger ensemble members?
In this case, the
I'm not sure.
ensemble, so before when you were showing.
Oh, going back to these examples, like this kind of.
Yeah, so do we now? Yeah.
We're now back at. So we had like, February, March, April, 850. I think what's confusing Jonathan in this case is they are the ensembles are already columns of whatever it is in that year.
Oh, okay.
Here,
Okay.
ensemble dimension is referring to just basically time.
Yeah, at this point, when we're like using these indices, we haven't created an ensemble yet. What we're going to use these indices to do is say like, hey Dash, when you do decide to build an ensemble, I want them to come from January.
Okay. So this, right, so this is like, or if you had like 1,000 years right now, you'd be telling it to do just divide it up into years. You know?
Yeah, exactly. Yeah.
You're sampling the prior.
Yeah, you're saying where should I sample prior to build an ensemble?
Okay, okay. And you can just pick any time, like it doesn't have to be like purely January, it can be like January of like 1800
Yeah.
and.
And it doesn't have to be like a monthly grid. This is just, that's why I left this generically as ensemble dimension. It can be anything. In this, you know, I personally work in the combinator a lot, so I kind of like made a little figure here, but like this is from that end-trend data set. You know, maybe we wanted to reconstruct Junes, then our reference indices would point to like each of these Junes, but again, it does not have to be that specific.
Right. The point being is you said it's sampling prior to create your own.
It's where you're sampling. Yeah, any more on reference indices? They're important.
Do you have the option to make averages? Like, say,
Yes.
you want
Yes,
to just.
we'll come to that in a second.
Okay.
Yeah, so just as a quick look under the hood, I've had people wonder like, hey, let's say I have a sequence where it's like December, January, February. And I make like the December's reference indices. am I gonna end up with like a bad state vector that like goes off the edge of the grid and like runs into a whole bunch of nans? The answer here is no. If Dash detects that you like go off the end of a grid, I'm sorry, off the end of a data catalog, then it won't allow an ensemble member to be built there. Also, I think typically we tend to just use the same reference points for each variable, because usually we just want to sample the same variables from like the same set of runs. If for some reason you did provide different reference points for the different variables, then Dash is going to find intersect. So like only the reference points that are common to all of the variables, and will only select ensemble members for it. I don't really think this will come up.
I am curious, because we're talking about how, okay, maybe you have precipitation, you want that, you want low, you want precipitation, but then for temperature, you only want the northern hemisphere, for instance. What is an example, like why would you only sample that one?
Well, maybe, so like with this end trend example, all of my proxies are like north of 35 north. So I just know that there's really no covariance, you know, that far south. So it's not really a place I should be trying to construct with that proxy. So I might as well just remove it.
Presumably that speeds things up too, right?
It does speed things up, yeah. Because now we have to process half of a spatial grid. Okay, so sequence indices. We're gonna start building off of those reference points. So we mentioned you might want to have a sequence through time, and how that's tricky because we're using time to select the ensemble members, but we also want time to have some sort of structure down the state vector. And so what sequence indices then, there are going to be a set of offsets that we give to our reference points. So this will be like a list. And what the list will do is, well, I guess I'll stay with the mouse, is you say, hey, maybe instead of, like, I want to select one ensemble member for each year. And I want that, but I want each ensemble member to, I guess in this example, have March and August. Why not? I don't want to build an ensemble member for March and separately an ensemble member for August. No, I want those two in the same ensemble. So the reference index gives us like a reference point to start building the sequence. If you're not implementing a sequence, you'll just build from the reference point. But if you do have a sequence, you'll say, okay, now from this reference point, I want you to include data that is, 1, 2 data indexes ahead along the time dimension, and also 2, 3, 4, 5, 6, 7 time points ahead. Yeah.
Why wouldn't you just start the reference point at March?
You should.
You should.
Yeah, totally. It'll be more readable. Sometimes what I'll do is I'll just select it January because it's the beginning of the calendar year, and then I like to later be like choose June, July, August, but you can do either. It's probably easier to do it with June. It's probably a little yeah. Yeah, so here's just kind of using that example again. Say here is our ensemble before with all these years that we're going to select ensemble members from, but we also want this monthly structure down the state vector variable. Then we're going to indicate a set of offsets. I think I said in this example, I'm selecting reference point at individual June months. So this is exactly what you were suggesting. So the offsets for June, July, and August would be +0, that's June. +1 index, it's July, and then +2. So August. You can also put negative indices in there. If I use June as a reference point and I actually want it to be like an April through August mean, then I would do -2. They don't need to be evenly spaced. They don't need to be ordered. They're just whatever you get.
So for clarity, you could say, okay, my reference indices are on January, but I want DJF, so it would be -1.
Yeah. Or if you're like, I want it to be DJF and also August, you do -1, 0, 1, like 8 or something. You don't have to include all the months. Yeah, and so going forward, I'll kind of refer to each of these like offsets along the sequence as a sequence element. So June is the first sequence element, it's got the +0 offset, July is the second sequence element, this one offset, etc. Questions and sequences. Promise we'll start actually with some stuff. The other time we might need some indices is when we're taking a mean over an ensemble dimension. So another way you could imagine building the state vector is like, instead of having like June, July, and August, I want my state vector to be a JJA mean, right? JJA. And so what I need Dash to do under the hood then is find data from those 3 months, but then take a mean over them. And so you're going to use something called mean indices to do this. The idea is very, very similar to the sequence indices. Again, we're just talking about a set of offsets relative to the reference point. So
We have one question in the chat.
oh, yes, so Claire asks for the DJF example. What would Dash do for the first year? There's no December, or the last year where there's no JF. Yeah, that's a great question. So as Dash goes through, it checks whether it's going to fall off of our data catalog or not. And if it would have to fall off the data catalog to make a sequence, it's not going to allow you to build an ensemble member there. So maybe I had 1,000 years and I'm doing this kind of DJF example. I would end up with an ensemble that has 998 ensemble members because it's not going to allow one for the first year where I don't have December. And it's not going to allow one for the last year where I don't have January and February. Does that answer your question, Claire? Cool. Great.
Somewhat related question, for something like a DJF or a JJA, with the months having different numbers of days, is that a weighted mean or is it just a straight up mean?
You can do both standard and weighted means. We'll talk about that in the code section. Yeah, so this is what you might look like with the time mean in your onsite. And again, the mean indices. So here I'm going back to that example where my reference points are the June months. I'm saying this time I'm going to take a June, July, August mean. Mean indices are again these offsets 0, 1, and 2, because that's where June, July, and August are located relative to June. The last thing is like what happens when you combine these two. And essentially, the process is find a reference point, find the sequence elements, and then apply the mean indices at each of those, apply the same mean indices at each of those sequence elements. This could be useful if you wanted like a series of seasonal means, where you want like JJA mean, but then also a, oh god, I lost track. Let's start over. You want a January, February, March mean. Cool. But then after that, you want April, May, June. And then after that, you went July, August, September. So you could stack time means in a sequence. And yeah, that's that. Does anyone have any question on combining? Cool. Okay, that's enough on kind of like these indices. Definitely time to jump into the next coding section. It's like we have a little bit of time for lunch, so this session might span lunch itself a little, but I think we'll go ahead and get started with it. So we're going to be using the state vector class to design and build our ensemble. And so the state vector class has this command state vector, and that's going to create a new state vector object. You can optionally use the first input to label the state vector. So to see what this looks like, might be like, I'm going to use SV as my state vector object. State vector. You can see like, okay, this is a state vector, doesn't have any variables in it, so it has a length of 0. Or similarly, I might give it a label like my demo. Like, cool. Now, if we look at this state vector, we can also see the label. Now, the next thing we want to do is we want to add some variables to the state vector. And as we discussed, each variable is going to be some subset of data from a grid file. So the command we're going to use here is state vector.add. kind of the syntax for this command is first input is going to be the name of a variable. The second input is going to be the grid file data catalog that variable's data is located in. We're going to refine what part of that data we use as we go on, but for now we just need to say like what file is it. And so as the second input, you can use a grid file object, or you can just use the name of the grid file itself. So for example, back here, I might be like state vector equals state vector dot add. I'm going to add in a temperature variable, and it's located, the data for that variable is located in temperature CSM catalog. So when we do this, okay, we can see there's some stuff going on in our state vector now. You can see it has some absurdly long length. Because it has some absurdly long variable named t for temperature in it. And the reason it's so long is when you add, like when you initialize a new variable, all of the dimensions of that variable are set as state dimensions. So the reason this one is so long is we're treating like all 13,872 time points as like a single ensemble member. And yeah, we'll refine that in a few steps. Actually, the next step.
So what is the coupling, right, like what is that?
Coupling means that when I select an ensemble member from year 5, all of the variables in the state vector will be selected from year 5, which is what you want. It means they're coming from the same point in time. I added in the option, you can turn that off if you want. It has never come up just yet, but
Yeah, I was just gonna ask what it would be like without.
I mean, if you did it without, you might have like temperature from year 5 and then precipitation from year 27, which they're not being sampled from the same point. So at this point, I don't know why you do that, but I'm sure the need will arise at some point. So it's in there to change.
And again, if you want to save this as like, a map file.
Yeah,
you can
let's-
center it in another map file or the same one or whatever.
Yeah, this is where the demos on the website, if you go to the bottom of the demo, there's the code for pretty much everything I'm going to do here. So yeah, feel free to copy that into a map file, and I'll write the script as we go along. It's a great idea. Here we might initialize state vector. Down. We're going to add some variables. Now, you can add multiple, if you have a state vector that has like a whole bunch of different variables in it, it'd be kind of a pain to be like state vector.add, state vector.add, state vector.add. So if you have a bunch of variables in the same data catalog, you can add multiple variables at once by making the first input a list of variable names. So if I want to like kind of start this over again, go back to an empty state vector, I could be like, state vector, I'm going to add in temperature from the northern hemisphere, some sort of temperature index, I don't know, a bunch of temperature variables. And then I can be like, oops. You see now this state vector would have like 3 variables in it. Again, absurdly long, but we would fix that eventually. The other thing is you're not limited to a single data catalog. You can add multiple variables from different catalogs. And this is really where, this is usually the step where you'll start to add in like multiple different climate variables, like maybe a temperature variable from a temperature catalog, a precipitation variable from a precipitation catalog, etc. The way you would do that is provide a list of variable names and then a list of grid files. So let's see. Where do I have the grid file? I have one in the other example. Zoom is in the way. Okay. So let's try. Again, I'm going to start over. Clear all my variables. The clear command kind of delete all the variables in the workspace. But I'm gonna do like state vector add temperature, which is in temperature CSM. Oops. So I forgot to create variables. There we go. And maybe I'll add a sea surface temperature variable from over this other demo. I have a data file in this. So we'll do like sea surface temperature, and that's over here from this sea surface temperature grid file. You can see like, oh, okay, cool. Here's our second variable. Do the second variable has a very different size. It's from our data catalog. Just emphasizing you can add multiple variables. If you call the state vector.add command like multiple times in a row, you can keep adding new variables. Alternatively, you can just combine it all into one command. So again, I'm just going to start everything over here. If you like state vector. You can combine it into one command by providing a list of variable names and then the list of data catalogs. So I might be like temperature, sea surface temperature, catalog 1, SEM, oops. Second one was SST, is the second catalog. I would just add it all at once. This is nice if you have like a list of variable names, you know what they go with, you can just kind of call them.
So Dash will know if we add a variable that is not in the catalog file, and it will just giving us.
Oh, so this is really important. The variable names that you're doing here, these are not, they don't need to be the names of like the variable in the netcdf file. If your grid file has the var dimension, it doesn't need to be the name of any variable there. These are state vector variables now. They can include multiple climate variables if we want.
Okay.
So these are just unique names that we're going to apply to some subset of our data catalogs.
So and that's why it's more organized to have each catalog file, grid file as
Yeah.
one variable.
Yeah, because then you can just give it the catalog and it knows which catalog it's reading from.
Yeah, and those names are up to you, it's just.
Yeah, it's completely up to you.
Choose whatever, if it's air temperature, you can say SAT, T. Whatever helps you remember it. Later, you'll be able to call them out, right, based on that.
Yeah, so I think in this demo that I did for ntrend, I said, I'm going to include I think I said the summer mean, like the June, July, August mean temperature field. I'm going to include a global temperature index, and then I'm also going to include the individual monthly fields in my state vector. So that would look like, here are my variables. I'm just going to give them some names. This will be T summer. I'll do JJA. This will be T index. T monthly. They're all different state vector variables. The catalog that they're in is sure sim grid. I'll call it catalog. Catalogs are really hard to type. And then to add them, here are my variables. And here's the catalog that these variables are in. How are people doing with this? Questions? Okay.
I just ask one more question.
Yeah.
It's like, so you said that the variable names you assign don't have to match what's in the data itself.
Correct.
So how, okay, so.
Like these variable names are just some name that you find convenient to call these things.
Okay.
So all you're doing here, Cynthia, is saying, I would like some variables, and this is where the information is going to be stored. But you haven't actually yet told it where it's drawing it from. So later you're going to go back and link it and be like, I want you to draw my temperature.
Like JJA is coming from
That's
the June, July,
it.
August portion.
Yeah,
Right, and I have to index that from the prior, like I have to sample that from the prior and
Yes.
fix the spirit.
Yes. Yeah, so again, just kind of, this is very like SV state vector object here. It's very much a design template It's letting you just shape what portion of the data catalog you're gonna pull out. Cool. So the next thing we need to do is we have this design command. The design command lets us kind of do two things at the same time. One, it's going to let us indicate which dimensions we should be using as ensemble dimensions. And it's also going to let us select the subset of grid file data that's needed for each variable. With the exception of sequences and means, which we'll see separate commands for those. But if you want to select like the northern hemisphere, this is where you're going to do it. Or if you want to select, you know, Januaries as your reference indices, this is where you're going to do it. So yeah, the command like syntax here is the first input is going to be the names of some variables in the state vector. You can also use -1 to select all the variables at once, which can be nice if you have a bunch of different variables. Dimensions, these are going to be the dimensions that you want to design, shape, and edit. And then the third input is going to indicate whether each of these dimensions is a state or an ensemble dimension. Yeah, so just for like what this would look like, let's go back to my example here. So I'm gonna start over. I'm gonna follow the everything in the script here. So there's our like 3 variables, and we have like some absurdly long state vector because time really should be an ensemble dimension. So like we're gonna select the ensemble dimensions. We do SV dot calling design commands. We would like time to be the ensemble dimension for all of these variables. So I'm just going to use -1 to select all the variables as the first input. Time is the dimension that we're editing. And we want it to be an ensemble dimension. If you look in the Dash documentation, you can see you can write this a bunch of different ways. You could put E, or I think it's false. No, it's 2. You can put 2 to select an ensemble dimension. Use what you like. I like to write out ensemble.
Is there a reason why you use the single quotes?
So in your example on the website, you do like a -1 dimensions type species.
Yep,
So
and
that's-
we're
is
gonna
that
we're gonna step to that in a second.
Okay.
But if I ran this command as is, you can see, hey, it updates that state vector, and now it's a much more reasonable length. That's because it's, you know, each variable is going to be latitude by longitude. That's it. You know, if you want to look in more detail at each variable, click this show details. You can see that time is an ensemble dimension. And then there's even more details. You can play around with those hyperlinks. See various things. Now, what if we want to select some reference indices? Well, in that case, we're going to use a 4th input, and this is going to indicate which elements along the grid file's time dimension that we should use as reference points for building a statement. So, kind of following in my demo here, what did I say we wanted to do? Let me remember. Okay, I said we're going to use January as a reference point for each state vector. And that way we'll be selecting, you know, data from each year or from different years when we sample out our ensemble. So you can use the grid file's metadata to select what you want. If you look back, so I'm going to go back and make another grid file object for the temperature CSM data catalog. There's that catalog. I'm going to return its metadata object. Oops. Forgot to be. Should have grid. And I specifically want to select January's. And if you recall, we can look at the time metadata And we'll remember I use MATLAB's like date time format. And I really like it because it lets you select by years or months of different types of time. So one thing we can do here is I'm going to select January's. So here's our grid file metadata. And you can string together commands like this, like you're doing grid file with its inputs, followed by the metadata command, and you use dot indexing to kind of chain these together. And then
How far can you change? Can I put a dot flat?
Yeah. that time. I'm gonna leave it, no, let's do it. Let's do it like this. Then we could do like January equals the month of the time point equals 1. This month command, when you give it a date time, like set the date time values, it'll give you like the month number. So like January is 1, February is 2, etc. And this is where I was kind of talking about, like, I think it's really good to try to keep your code like readable to humans. Instead of writing like, I could do like January is 1 in steps of 12 to like 13, 8, 6, something, right? But that's not great for a human read, right? So yeah, I think these using the metadata to select your indices is very useful. But what we could do then with this is that's going to be our 4th input. If I kind of rerun all of this code, now my state vector will only select, will only use January as a reference point. It's building different ensemble groups. We're at a good, it's gonna be a good spot to like break for lunch. I'll just mention 1 or 2 other things here. You can put in multiple different dimensions at once. Like maybe I had a run time dimension. I might do like run and time. I want them both to be ensemble dimensions. Okay, that's something you can do. Maybe I want to design the latitude variable so that we're only in the northern hemisphere. I also want to design time so that it's an ensemble dimension. And I can do like state. The second one's an ensemble. Like that. You can also provide indices for both of these at the same time by grouping them in a cell. So in MATLAB, you can use a cell that's a curly brace to like group things that are for different sizes. So I'll give an example of this. Let's do the northern hemisphere example. I'm going to pull this back to meta. It'll be a little easier to read. Time. I'm going to say the northern hemisphere, maybe it's New Hampshire, sure. It's metadata, the latitude metadata where it's above the equator. If I run this code, you can just look over here in the workspace. You see January is like very, very long. We can see that New Hampshire is much shorter. Yeah, the northern hemisphere is much shorter. You can't group them into an array with square braces in MATLAB. I'm going to appear my console. If I try to do that, it's going to be mad because they're different sizes. But you can group them with curly braces. It's a cell array. Each cell is holding something of a different size. Coming back to the design command, if I wanted to design both of these variables at the same time, I could go hemisphere and January. So if we ran the code up to this point, look at our state vector, we can see that there's 96 latitude points and time is like really long because it should be an ensemble dimension. But then when we run this code, cool, latitude is still a state dimension, but it's only 48 points now, 48 points in the northern hemisphere. And likewise, time is not listed on here anymore because it's been changed into an ensemble dimension.
So Jonathan, sorry, but the -1 just applies this to all the variables.
Every variable in the state vector.
That's what it, that's.
That's what that does.
Could
We
could
could,
that be a different, why is it -1?
well, so you can select variables using a couple different things here. So I'm gonna reset everything again. One way I could do this, is I could do state vector.design. Just the JJA variable. Latitude, still state dimension. Oh, if you're not selecting an ensemble dimension, you just use an empty array. Let's do that here. In the northern hemisphere. And you can see that in this case, just the JJA variable has been like restricted to the northern hemisphere. But a different way I could do this is instead of writing TJJA, TJJA is the first variable in the state vector. So I could just do it with its variable index, which is 1, it's the first variable. And that would do the same thing. And this can be nice. Sometimes, in some cases, I'll add in a variable for each proxy record because I want a very, very small subset of a climate field to feed into the forward models. And using those indices can be nicer than having to track the names of like every proxy record that I'm throwing in. Yeah, so the reason it's -1 then is because -1 is not a valid index in MATLAB, so you can't accidentally, you wouldn't accidentally index into a real variable and get them. Yeah, that's fine.
Okay, but it's the equivalent of saying all.
All of it. Yeah.
Okay.
Cool.
The empty array,
An empty array is like 2 square brackets.
or why is it in the last command that you?
Oh, right. So by default, every dimension is initialized as a state dimension, right? And in this case, I just want latitude to stay as a state dimension. I'm not selecting an ensemble dimension here. If you're not selecting an ensemble dimension, you can just leave the third input empty. The third input is all about saying like who's an ensemble and who's a state.
But you could also just stay there.
Yeah, you could also write state there. That would be exactly the same. Actually, it wouldn't be exactly the same. If I remember right, the empty bracket puts your dimension in whatever state it was already in. So if it was an ensemble dimension, it wouldn't flip it back, it would just leave it as it is. I think, let me double check that. Sure, I'm telling you right. Yeah, you can use empty brackets, you can use a 0 to do the same thing. You can also write out current to leave its dimension in its current state.
But you could write state.
Yeah, in this case, it wouldn't because latitude was already the same expression. Yeah, I think that's our break point. You can do like any questions people have about design, but like I would suggest you go one.
One quick question for .NET.
Yeah.
So if you, in case we wanted to have 2 variables from the first grid file with 1 variable from the second grid file, do we have to repeat the first grid file for the catalog?
If you want to put in like 3 variables from 1 grid file, you could just put in the catalog once. But if you wanted 3 variables and 2 of them were from the same grid file, you need to do grid file 1, grid file 2, and then grid file 2, because the size of the list needs to match up with the other list. Yeah.
How are people doing? Are you with us? Are you lost? Okay,
Basically, this allows you to create this multitude of state vectors without ever touching
Data, or needing to reshape the data.
every shaping, manipulating beforehand. So it's all programmatic at the same time.
Do you have any utilities for dimension reduction? Do you have any utilities for dimension reduction? Sometimes you do an SVD, state like that with 1,000.
You mean like running, yeah, doing like an EOF?
Yeah,
You would need to run it in advance, but then you could make it to a catalog of like EOFs that we computed. But yeah, the SVD is not built into the state vector class. That's strictly about reading out of the catalog.
No, they need total instead of mean. Can't remember. Like if you wanted to the total of the precipitation in JJA. You do that.
Total.
So add 3 months instead of taking.
I don't have that. It's-
Promise of the year.
So practically,
Yep,
like,
it was-
you can use this function to set up like. You know, like when I'm using it, I usually am pulling out, I want monthly SST in my state vector because I want to use that for my PSM, so I'm gonna pull that out, but then I'm gonna have also annual SST as a separate component of my state vector. That's ultimately what I want to get out of my reconstruction. So you can use this both to put in the variables you want to update, but also the variables that you need for your forward model, so. And you're gonna want the variables that you need for your current models. If you don't, if we get to later, even if, like, let's say I need like monthly SST for my forward models, but I don't really trust that I can reconstruct monthly SST. When we run the calendar filter, you don't have to update everything in your state. You can choose, you can pull out just one thing to update and save computational time, so. But you still want all those variables in there so you can run your system. That makes sense.
Yeah, it really lets you sort between the reconstruction targets, which is what the algorithm needs, and your forward model inputs, which often don't need to update.
Earlier, you showed like the conversion from Kelvin to Celsius. like,
Yeah.
in the metadata, has that been taken into account?
Yeah, so when after lunch, we're gonna come back and we're gonna look at the command, which is when like dash like looks at the design template and it's like, great, let me find the data and make your ensemble. So what it'll do is it'll go to the grid file and it's like, hey, I want this data. And that catalog has that transformation. So when it picks up the data, it's gonna apply the transformation and then it will pass it to state vector.
So it's in-
Yeah, like you won't have to do anything to implement that transformation. If it's in the data catalog, it'll just automatically do it.
Yeah, so we didn't cover it, but you can actually automatically do that transformation by coding it into the grid file. And that's what Jonathan already did.
I think just does
Figured
like,
out CSM grid, you know.
and you do like log transforms sometimes, so like that's another transformation that's in the grid file is you know,
Yeah.
when it loads data, it'll take the raw data out of the output file, then it'll log transform it, that's what that's the dash.
I think it can now do like a weighted mean.
Yeah, we
There
can,
are a lot of functionality, so you might need that for isotopes, for example, you usually do precipitation weighted. And mean for delta weighting to precip, and yeah, there's all this stuff in the
Here
documentation.
are all our different like types of transformations that are supported in the catalog. And then separately, state vector can take means and weighted means over these transform values.
You can also, if you want to do something to your data that's more complex, you can do that outside of
Mhm.
the dash toolbox.
That would be like what Dan mentioned, where like maybe
Yeah.
you wanted to take an SVD.
Yeah,
That's kind of outside of the scope of Dash, but you can totally do that, and then that's your.
just need to save that transformation somewhere.
Yeah,
In
that's
that
another-
CDF or a map file. Isn't intermediate.
Can you like retroactively go back and change the
Yes.
file?
Yeah, so if you load up. Yeah, if you load up your grid file object, call the transform command again, and now if you. Maybe you built your first state vector ensemble, you go back and you change the transform, now if you rebuild the state vector ensemble, it'll look different as you do the transformation.
But any transformation you have to do is the catalog PSNs.
Well, yeah. I mean, Dash doesn't know what PSM you're gonna use, so it's just gonna try to apply whatever transformation you gave it. The PSMs though, like if you give complex values for like baselines, and like, nope. So
Yeah, these are
you'll get
more,
errors when you actually try to run the forward model.
these are more like. In my view, these are things that I do, so I will take a log of precip and update in log space, and so I might wanna do, so stuff I'm doing to the field that I don't. It's not necessarily related to the PSM.
Right.
If you need to transfer something to the PSM, that's in the PSM, right? So the PSM knows like, if you have a PSM that's a nonlinear function of something, then that's all over there. So this is more like Like I also use this, like I said, to take like the annual mean weighting and preset weighted. Right? You need to do that transformation here. If you just want to update the annual mean of weighting and preset. Because it's a weighted average, so. And you don't get that out, like, as you know, if you actually look at isotopes and ICSM, it's like 8. There's like 8 components to calculate weighting and preset. So if you wanted to add those all up and then use that, you can do that in this step here. Rather than having to do that ahead of time and saving a separate like post-process file. So you can add up all those 8 terms. But dynamically. It's kind of a nice thing. That I asked Jonathan to build. Because I'm working with isotopes, so yeah. And same thing with the O18 seawater field, which is typically given as a ratio. You want to do a quick transformation to per mil, you would do that with this step. So then you don't have to worry about it.
I'll also mention another thing that's in gridfile, we need to get into it too much today, but you can do, if anyone's familiar with NCF operators, you can do like basic algebra across different data catalogs, but only basic algebra. So this is nice for CSM where like precipitation split often is like convective precipitation and what's the else? Large scale, yeah. You can, you'll have different sets of output files, build a catalog and just have, you can have dash just have them together.
All right, the break for lunch. Molly time.
For the bracket, with the 2 criteria. Anyone need to like try my use of that, but I guess that's.
So here, you try to get 2 sets of indices.
When do you guys want to come back for the Zoom?
Although
1:15?
that's not where the error
Huh?
is.
Yeah.
1?
Like, I feel well, it's all this stuff.
Okay, all right.
That actually, that can be.
Yesterday we were more than finished at 1, so.
Wait, can you